Mars has weathered 4 billion years of cosmic bombardment, survived massive asteroid impacts that would have sterilized Earth, and endured global dust storms that could swallow entire continents. The red planet has seen ice ages that lasted millions of years, volcanic eruptions that dwarfed anything in terrestrial history, and atmospheric loss that stripped away what might once have been an ocean world. But in all its ancient history, Mars has never faced anything quite like what approaches on October 3, 2025. 3I tell us, the designation alone carries an ominous weight that astronomers rarely acknowledge in public. The 3I marks it as only the third confirmed interstellar object ever detected entering our solar system, a cosmic refugee carrying the chemical signatures of stellar environments that may no longer exist. But Atlas isn't content to play the role of distant curiosity, visible only through the most powerful telescopes. This interstellar wanderer is writing its own rules as it approaches Mars, displaying behavior that has transformed routine astronomical observation into something approaching crisis management. The date matters more than most people realize. October 3, 2025 represents a convergence of circumstances that will never occur again in human history. Atlas will sweep past Mars at a distance of roughly 30 million kilometers, close enough that its gravitational influence could nudge debris into trajectories that intersect with the red planet for decades to come. But distance becomes irrelevant when dealing with an object that has been throwing cosmic tantrums since we first spotted it, generating a carbon dioxide coma of staggering proportions that extends millions of kilometers in every direction. The European Space Agency has been tracking this encounter with the kind of nervous precision usually reserved for defusing bombs. Their calculations paint a picture of celestial mechanics gone slightly mad, an interstellar visitor that refuses to follow the polite behavioral patterns we've come to expect from objects in our cosmic neighborhood. Atlas has been generating emissions that dwarf anything previously observed, brightness surges that arrive without warning and fade just as suddenly, creating spectroscopic signatures that don't match any models in our databases. But here's what keeps planetary defense specialists awake at night. The timing couldn't be more sinister if it had been planned by some malevolent cosmic intelligence. Just as Atlas reaches its closest approach to Mars, solar conjunction will render clear observation nearly impossible for several weeks. We'll be essentially flying blind during the most critical phase of the encounter, trying to monitor a potentially catastrophic event through the cosmic equivalent of a keyhole while wearing a blindfold. NASA's Sphere-X telescope has been working overtime to catalog these anomalies, and the data creates a picture that would make any rational person reach for something stronger than coffee. The plume geometry looks fundamentally wrong. The gas emissions follow patterns that violate established models of cometary behavior. Even the orbit itself carries subtle perturbations that suggest Atlas isn't just a simple chunk of dirty ice from the outer reaches of another star system. Consider what we're really facing here. Most comets are gravitationally bound to their parent star, following predictable elliptical orbits that bring them periodically close to their sun before sending them back to the cold darkness of the outer system. But Atlas is different. It's a true wanderer following a hyperbolic trajectory that will carry it past our sun and back into the void between stars. This isn't just a visitor from another solar system, it's a messenger from the deep cosmos, carrying within its nucleus the frozen chemistry of stellar environments that operated under conditions our solar system has never experienced. The massive carbon dioxide coma isn't just unusual, it's unprecedented. Most comets save their dramatic displays for when they're much closer to the sun, but Atlas seems to have missed that particular memo from the Cosmic Etiquette Handbook. It's been venting material at rates that suggest either internal instability or processes we don't understand, creating a billowing shroud of gas that makes detailed observation of the actual nucleus nearly impossible. This is where the scenario becomes genuinely concerning for anyone who understands orbital mechanics. As Atlas approaches its closest point to Mars, we're not just dealing with a single object following a predictable path. We're potentially witnessing the prelude to a fragmentation event, the moment when a comet that has held itself together through 30,000 years of interstellar travel finally succumbs to the thermal and gravitational stresses of solar system entry. Picture this nightmare scenario unfolding in slow motion. Atlas, stressed beyond its structural limits by solar heating and gravitational forces, begins coming apart just as it reaches Mars's gravitational neighborhood. The parent body might continue on its predictable trajectory, passing harmlessly by the red planet, but the fragments would write their own rules. Each piece of debris would carry its own momentum, modified by the chaotic forces of the breakup event. Some might accelerate toward the sun, others might be deflected outward toward the stars, but a few, perhaps just a handful, out of hundreds of fragments, might find their trajectories bent, just enough by Mars's gravitational influence to transform a near miss into a direct hit. The European Space Agency's models suggest that even without direct impact, gravitational perturbations from a major fragmentation event could nudge debris into orbital paths that intersect with Mars's trajectory for years or even decades to come. We might be witnessing not just a single close encounter, but the seeding of a cosmic minefield that will plague Mars exploration efforts for generations. What makes this scenario particularly unsettling is our fundamental ignorance about Atlas's true nature. The massive coma obscures our view of the actual nucleus, leaving us to guess whether we're dealing with a single massive object, a loose collection of fragments already barely held together by gravity, or something even more exotic. The glowing shroud that makes Atlas so visually spectacular might be hiding a cosmic time bomb whose detonation could scatter debris across multiple planetary orbits. NASA's Science Mission Directorate has been conspicuously quiet about specific contingency plans, though sources within the agency suggest that multiple Mars orbiters are being positioned to capture whatever data they can during the encounter. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Trace Gas Orbiter represent humanity's eyes and ears at Mars. If something dramatic occurs on October 3rd, these robotic sentinels will be our only witnesses to events that could reshape our understanding of interstellar visitors. But even these sophisticated instruments operate under significant constraints. Their cameras and spectrometers were designed to study Mars, not to track high-velocity cosmic debris. Their communication systems were built for routine data transmission, not for emergency broadcasts about planetary catastrophes. If Atlas decides to put on a truly spectacular show, our Mars-based assets might find themselves woefully unprepared for the cosmic fireworks. The promise of this investigation extends far beyond mere scientific curiosity. We're going to follow the evidence wherever it leads, even if it takes us into territories that make comfortable assumptions about planetary safety seem dangerously naive. We'll examine collision scenarios that could create craters visible from Earth. We'll explore atmospheric effects that could turn Mars into a radioactive wasteland. We'll consider contamination possibilities that could complicate humanity's plans for Mars colonization for centuries to come. Most importantly, we'll ask the questions that official agencies seem reluctant to pose in public. What if Atlas isn't just passing by? What if October 3rd marks the beginning of something far more sinister than a simple gravitational encounter? What if the worst-case scenario isn't impact at all, but something far more subtle and potentially permanent? The answers might surprise you. They might terrify you. But one thing is certain. After October 3rd, nothing about our relationship with interstellar visitors will ever be quite the same. The collision scenario we're about to explore represents just the tip of a cosmic iceberg that extends far deeper into the realm of planetary catastrophe than most people dare to imagine. Atlas defies every comfortable assumption we've made about interstellar visitors. When Oumuamua swept through our solar system in 2017, it behaved like a well-mannered cosmic tourist, following predictable physics, responding to solar radiation pressure in ways our models could explain, and departing quietly without causing any fuss. But Atlas operates by different rules entirely, rules that seem designed to keep astronomers awake at night, wondering what they're missing. The first anomaly emerged within weeks of Atlas's discovery. Spectroscopic analysis revealed a carbon dioxide emission rate that violated every model in the astronomical databases. Most comets gradually increase their gas production as they approach the Sun, following smooth curves that reflect the physics of ice sublimation under increasing solar radiation. Atlas, however, has been throwing irregular outbursts that spike and fade without apparent correlation to its distance from the Sun or any other predictable variable. These aren't gentle variations in emission rates. We're talking about sudden brightness increases that make Atlas temporarily visible to amateur astronomers, with backyard telescopes, followed by equally dramatic fade-outs that return it to the realm of professional observatory observation. The energy requirements for such displays suggest internal processes that conventional comet models simply can't explain. The European Space Agency's initial trajectory calculations assumed they were dealing with a typical interstellar object. Dense, relatively small, following ballistic physics as it passed through our solar system. But Atlas's actual behavior has forced repeated revisions to these predictions, each one revealing new complexities that push the object further outside the bounds of normal astronomical experience. Consider the size estimates alone. Early observations suggested a nucleus perhaps a few hundred meters across, similar to other interstellar visitors. But the massive Comet production indicates either a much larger object than initially calculated, or composition unlike anything we've previously encountered. The amount of material Atlas has been venting should have depleted a small nucleus months ago, yet the emissions continue unabated. NASA's James Webb Space Telescope conducted infrared observations in August that remain under analysis, but preliminary results have done nothing to clarify Atlas's true nature. The infrared signatures reveal complex chemistry involving not just carbon dioxide and water vapor, but organic compounds that don't match the inventory of any known solar system object. These aren't just exotic molecules, they're molecular structures that suggest formation under stellar conditions completely unlike those in our cosmic neighborhood. The orbital mechanics present their own puzzle. While Atlas follows the expected hyperbolic trajectory of an interstellar visitor, subtle variations in its path suggest non-gravitational forces that exceed what solar radiation pressure alone could account for. These anomalous accelerations could result from asymmetric outgassing, but the patterns don't match conventional jet models used to explain similar effects in solar system comets. More disturbing is the discovery of what mission scientists diplomatically describe as structural anomalies in radar observations. Ground-based radar facilities have detected reflection patterns that suggest Atlas might not be a single coherent object, but rather a loose collection of components held together by minimal gravitational attraction. If accurate, this loose rubble pile structure makes fragmentation during the Mars encounter not just possible but probable. The chemistry revealed by spectroscopic analysis tells a story of formation under conditions that never existed in our solar system. Isotopic ratios in the detected gases indicate processing by stellar winds from a star, type different from our Sun, possibly a red giant or asymptotic giant branch star in its final evolutionary phases. The organic compounds show signs of radiation processing over timescales measured in tens of thousands of years, suggesting Atlas has been wandering the interstellar medium far longer than initially estimated. But perhaps most unsettling are the temporal patterns in Atlas's emissions. Professional observatories monitoring the object have detected what can only be described as periodic variations in gas production that follow no known astronomical phenomena. These variations occur on timescales ranging from hours to weeks, suggesting active processes within the nucleus that respond to triggers we haven't identified. The massive scale of the coma itself presents observational challenges that hamper detailed analysis. At its maximum extent, Atlas's carbon dioxide envelope spans several million kilometers, larger than some planetary magnetospheres. This creates an observational environment where traditional techniques for studying comet nuclei become ineffective, leaving astronomers to infer the object's properties from the characteristics of its emissions. Temperature measurements of the coma reveal another anomaly. The gas temperatures don't match models for sublimation-driven emission, instead showing characteristics that suggest active chemistry within the coma itself. Complex organic molecules are forming and dissociating in real time as Atlas approaches the Sun, creating a dynamic chemical environment, unlike anything previously observed in interstellar objects. The magnetic field interactions present yet another puzzle. Mars's weak magnetic field should have minimal influence on Atlas's charged emissions, but magnetometer readings from Mars orbiting spacecraft have detected perturbations that begin weeks before closest approach. These magnetic anomalies suggest that Atlas carries its own electromagnetic signature, possibly the result of charged particle interactions during its interstellar journey. Ground-based observations using the world's most powerful telescopes have revealed structural details that don't fit standard comet morphology. Instead of the typical spherical or elongated nucleus expected from gravitational collapse, Atlas appears to have an irregular, possibly compound structure that might represent multiple objects orbiting in close formation. This configuration would be inherently unstable, making breakup during solar system passage not just possible but inevitable. The dust production patterns add another layer of complexity. Traditional comets produce dust through mechanical processes as ice sublimes and releases embedded rocky particles. But Atlas's dust emissions show size distributions and chemical compositions that suggest more violent ejection mechanisms, possibly explosive outgassing or surface fracturing under thermal stress. International space agencies have quietly implemented enhanced monitoring protocols that go far beyond routine astronomical observation. The coordination between NASA, ESA, JAXA, and other organizations represents the most comprehensive tracking effort ever mounted for a single interstellar object, suggesting that official concerns about Atlas extend beyond academic curiosity. Amateur astronomers worldwide have contributed observations that professional facilities might miss due to scheduling constraints, but their data only deepens the mystery. Long-term monitoring by dedicated amateur observers has revealed emission patterns that suggest Atlas might be responding to solar wind variations or other interplanetary phenomena in ways that indicate internal structure, far more complex than a simple ice and rock amalgamation. The implications extend beyond mere scientific curiosity. If Atlas represents a new category of interstellar object, one that challenges our understanding of how such visitors behave in solar system environments, then our models for predicting and managing encounters with future interstellar visitors may be fundamentally inadequate. We might be witnessing not just an unusual astronomical event, but the first example of a class of cosmic phenomena that could reshape our approach to planetary defense. As Atlas continues its approach toward Mars, each new observation adds complexity rather than clarity to our understanding. The object that seemed mysterious but manageable when first detected has evolved into something that defies comfortable categorization. We're no longer dealing with a routine interstellar visitor following predictable physics. We're tracking a cosmic wildcard whose behavior suggests capabilities and characteristics that push the boundaries of what we thought possible for objects wandering between the stars. The anatomy of this potential destruction lies not just in Atlas's size or composition, but in its unpredictability. We're approaching October 3rd with an interstellar visitor whose true nature remains fundamentally unknown, whose behavior defies modeling, and whose interaction with Mars could produce outcomes that no amount of theoretical analysis can fully predict. This isn't just a close encounter. It's humanity's first test of how well we understand cosmic threats that originate beyond our solar neighborhood. The mathematics of cosmic destruction follow elegant equations that can calculate the end of worlds with the same precision we use to plan grocery shopping. When astronomers run the numbers on Atlas potentially striking Mars, the calculations initially seem reassuring. At a closest approach distance of 30 million kilometers, direct collision probabilities fall somewhere between astronomically unlikely and physically impossible. But mathematics, like democracy, works best when everyone follows the rules. And Atlas, as we've established, appears to be something of a cosmic anarchist. Consider the energy scales involved in even a fragment impact. A piece of Atlas measuring just 100 meters across, roughly the size of a city block, would arrive at Mars, traveling at velocities that make rifle bullets look sluggish. The kinetic energy involved would equal thousands of nuclear weapons detonating simultaneously, but delivered as a concentrated package rather than the distributed explosion of atmospheric nuclear detonation. Mars's atmosphere offers virtually no protection against such cosmic artillery, unlike Earth's thick atmospheric blanket, which can burn up smaller objects and significantly slow larger ones. Mars's tenuous envelope might as well be vacuum for the purposes of stopping interstellar projectiles. The impact energy that would be partially absorbed and distributed by Earth's atmosphere would instead be delivered directly to the Martian surface with undiminished fury. The resulting crater would span several kilometers, but that's merely the beginning of Mars's troubles. The impact would excavate millions of tons of subsurface material, instantly vaporizing any permafrost and sending shock waves racing through the planet's crust at speeds that would make the worst earthquakes in terrestrial history seem like gentle tremors. The seismic effects alone could trigger landslides across entire hemispheres and potentially destabilize geological formations that have remained unchanged for billions of years. Impact ejecta, pulverized rock and ancient ice, hurled high into the tenuous atmosphere, would create a planet-wide dust storm that would make the seasonal tempests we've observed look like gentle spring breezes. Within hours, the entire planet would be shrouded in a choking veil of suspended particles that would persist for months or even years. Solar panels on rovers and landers would become useless. Starved of the sunlight they need to function, temperatures would plummet as dust blocked incoming solar radiation, triggering a nuclear winter effect that could fundamentally alter Mars's climate for decades. But let's escalate this scenario to truly apocalyptic proportions. What if Atlas doesn't just shed a single fragment, but undergoes complete fragmentation as it approaches Mars? Picture dozens of city block-sized projectiles following slightly different trajectories, each carrying enough kinetic energy to excavate craters that would be visible from Earth-based telescopes. The cumulative effects would push Mars beyond a mere bad day into the realm of planetary catastrophe. Multiple impacts would create overlapping ejecta clouds, turning the entire planet into a chaotic maelstrom of debris. The combined electromagnetic effects would create radio blackouts lasting for months. The dust opacity would reach levels that completely block solar radiation, triggering a planetary ice age that could alter Mars's climate for centuries. The radiation environment would spike dramatically as impacts excavate subsurface materials and loft them high into the atmosphere. The thin atmospheric layer that provides Mars with minimal radiation shielding would become saturated with charged particles, creating hazardous conditions that would make the planet uninhabitable for any future human explorers. Even our hardiest robotic systems would face increased risk of radiation-induced failures, potentially ending decades of successful Mars exploration in a matter of hours. Now consider the gravitational chaos that multiple impacts could unleash on Mars's two small moons. Phobos and Deimos, already irregular chunks of rock with questionable gravitational stability, could find their orbits perturbed by the seismic shock waves and debris clouds from surface impacts. Phobos, already on a gradual death spiral that will eventually crash into Mars in about 50 million years, could have this timeline accelerated dramatically. If impact ejecta were to strike Phobos with sufficient force, or if gravitational perturbations from multiple surface explosions were to destabilize its orbit, we could witness the destruction of a moon in real time. The debris from such an event would create a ring system around Mars, but not the elegant, stable rings of Saturn. Instead, we'd be looking at a chaotic cloud of rocky fragments that would pose navigation hazards for centuries to come. The electromagnetic pulse generated by multiple simultaneous impacts would create a phenomenon unlike anything in the historical record. As expanding fireballs interact with Mars's weak magnetic field, they would generate intense electromagnetic radiation capable of inducing damaging currents in electronic systems. Every piece of human technology in Mars orbit would simultaneously face conditions more hostile than anything their designers ever anticipated. Star trackers would lose their ability to navigate as charged particle clouds interfere with stellar observations. Communication systems would be overwhelmed by radio frequency interference from ionized debris. Solar arrays would suffer damage from high-velocity particles accelerated by the impacts. On the surface, the consequences would be even more severe. The spacecraft designed to weather normal Martian dust storms encounter conditions that fall completely outside their operational parameters. The long-term atmospheric effects would be profound and potentially permanent on human timescales. Mars's current atmospheric system exists in a delicate equilibrium that has persisted for millions of years. The massive injection of vaporized subsurface materials, exotic gases from Atlas's nucleus, and the thermal shock of multiple simultaneous impacts could destabilize this system completely. We might witness the birth of weather patterns that have no precedent in Mars's recorded history. Temperature differentials created by impact heating could drive atmospheric circulation that makes the planet's current global dust storms seem quaint by comparison. The chemical composition of the atmosphere itself could be altered by materials excavated from deep within Mars's crust, regions that haven't interacted with the surface environment since the planet's formation. But perhaps most devastatingly, multiple impacts would transform Mars from humanity's most accessible stepping stone to the outer solar system into a radiation-soaked wasteland orbited by the debris of its own destroyed moon. The psychological impact on Earth would be immediate and profound. Mars represents our next frontier, our backup plan, our second chance at becoming a spacefaring civilization. To watch it transformed into an uninhabitable hellscape would be like watching our future crumble in real time. The ripple effects would extend far beyond scientific disappointment. Stock markets would plunge as aerospace companies saw their Mars exploration contracts evaporate overnight. Congressional hearings would demand answers that no one could provide. The carefully cultivated public support for space exploration, built up over decades of successful missions and stunning imagery, could evaporate as people questioned whether expanding beyond Earth was worth the cosmic risks. International Mars exploration treaties would become obsolete overnight as the planet they were designed to govern became too dangerous to visit. Private space companies that had invested billions in Mars transportation systems would find their business models destroyed by cosmic accident. The dreams of Mars colonization, which had seemed tantalizingly close to reality in the 2020s, would be replaced by the grim necessity of developing completely different strategies for human expansion into space. Yet even this catastrophic impact scenario assumes we understand what Atlas is and how it behaves. What if the real threat isn't mechanical destruction from high-velocity impacts, but something far more subtle and potentially more dangerous? What if Atlas delivers not just kinetic energy, but exotic chemistry that could poison Mars's potential for human habitation in ways we're only beginning to understand? The electromagnetic shockwave scenario we're about to explore doesn't require a single fragment to actually strike the planet, but could prove even more devastating to humanity's long-term relationship with the red world. Forget everything you think you know about cosmic impacts and planetary destruction. The most insidious threats from Atlas might never actually touch Mars at all. Instead, we could be witnessing the prelude to an electromagnetic catastrophe that operates through mechanisms more subtle than kinetic energy, but potentially more devastating than any crater-forming collision. Mars stands naked before the cosmos in ways that make Earth dwellers uncomfortable to contemplate. Unlike our home planet, which wraps itself in a protective magnetic cocoon that deflects most charged particles, Mars lost its global magnetic field billions of years ago. What remains are scattered magnetic anomalies, cosmic scars that serve as tombstones for the planet's former protective shield. This magnetic nakedness makes Mars exquisitely vulnerable to effects that Earth's magnetosphere would shrug off without breaking a magnetic sweat. When Atlas sweeps past Mars trailing its enormous carbon dioxide coma and potentially shedding debris, it won't be delivering a conventional shockwave in the Hollywood sense. There won't be a wall of compressed air racing across the Martian landscape at supersonic speeds. Instead, we're looking at something far more subtle and potentially more devastating, an electromagnetic and particle cascade that could fundamentally alter Mars's atmospheric chemistry and electrical environment for months or even years. Picture Atlas as it approaches Mars, its nucleus venting gases and particles in the chaotic bursts we've been documenting throughout 2025. Each outburst creates expanding clouds of ionized material, essentially plasma, that interact with the solar wind in complex ways. As this ionized cocktail encounters Mars's weak magnetic field remnants, it doesn't simply bounce off, it penetrates. It swirls, it creates electromagnetic eddies that can persist long after Atlas itself has continued on its trajectory toward the outer solar system. The immediate effect would be a dramatic enhancement of Mars's already meager auroral displays. Instead of the faint, localized glows that Mars occasionally produces, we might witness planet-wide light shows as charged particles from Atlas's coma cascade into the upper atmosphere. These auroras wouldn't be the gentle romantic displays that northern Europeans enjoy. They'd be angry, chaotic storms of light that would interfere with radio communications and potentially damage sensitive electronic equipment. But the visible effects represent only the tip of the electromagnetic iceberg. The real chaos would occur in Mars's ionosphere, the electrically charged layer of the upper atmosphere that our orbiting spacecraft rely on for communications. As Atlas's charged particles interact with this region, they would create radio blackout conditions that could last for weeks or even months. Think about the implications for our robotic explorers. The Mars rovers have grown accustomed to reliable communication windows with Earth, carefully scheduled sessions where they upload their discoveries and download new instructions. An ionospheric disruption could sever these digital lifelines, leaving billion-dollar robots effectively stranded on an alien world, unable to report their status or receive guidance from their human controllers. The electromagnetic chaos wouldn't stop at the ionosphere. Mars's thin atmosphere makes it particularly susceptible to electrostatic effects that would barely register on a world with a robust atmospheric envelope. As Atlas's debris field interacts with the Martian environment, it could create conditions similar to the massive dust devils that already plague the planet, but supercharged with electrical potential. Imagine dust storms where individual particles carry significant electrical charges, creating lightning displays that dwarf anything Earth has ever witnessed. These wouldn't be the relatively gentle static discharges we observe in terrestrial thunderstorms. They'd be violent arcs of electrical energy capable of damaging surface equipment and creating radio frequency interference that would make communication with Earth virtually impossible. The scenario becomes genuinely alarming when we consider Mars's propensity for global dust storms. These planet-wide tempests can begin from seemingly minor triggers, a small temperature differential here, a pressure change there. The electromagnetic chaos from Atlas's passage could provide exactly the kind of trigger needed to nudge Mars's atmospheric system over the edge into one of these global catastrophes. But here's where atmospheric physics gets truly disturbing. What if Atlas's passage doesn't just trigger a conventional dust storm but creates something entirely new in the annals of planetary meteorology? What if the combination of charged particles from the comet's coma and Mars's existing atmospheric dynamics creates a feedback loop that becomes self-sustaining? Picture this nightmare scenario. Atlas's charged debris creates initial electromagnetic disturbances in Mars's upper atmosphere. These disturbances generate static electricity in the lower atmosphere, which charges dust particles and makes them more likely to become airborne. The increased dust loading alters the planet's energy balance, creating temperature and pressure differentials that sustain the storm. Meanwhile, the charged dust particles continue to interact with what remains of Mars's magnetic field, perpetuating the electromagnetic chaos. The result would be a planet trapped in a quasi-permanent state of electromagnetic and meteorological turmoil. A feedback loop from hell that could persist for years after Atlas has continued on its journey toward the outer solar system. Mars would become a world where dust storms never end, where radio communications are sporadic at best, and where the radiation environment is so chaotic that even our hardiest robotic explorers might succumb to electronic failures. NASA's spacecraft designers have anticipated many challenges for Mars operations, but they've never had to contend with a planet-wide electromagnetic tornado. The Mars Reconnaissance Orbiter's high-gain antenna might find itself constantly fighting interference from charged dust clouds. MAVEN's particle detectors, designed to study the gentle solar wind interactions with Mars's upper atmosphere, might be overwhelmed by the chaotic particle environment created by Atlas's passage. The public relations nightmare would be immediate and profound. As images from Mars become sporadic and communication windows disappear, speculation would run wild. Social media would explode with theories about what's really happening to our robotic emissaries on the red planet. Official denials and technical explanations would be drowned out by more sensational narratives about cosmic catastrophes and government cover-ups. But perhaps the most unsettling aspect of this electromagnetic scenario is how it would be misunderstood by the general public. Mars wouldn't actually be on fire in any conventional sense. Carbon dioxide doesn't support combustion the way oxygen does. But the global auroral displays, the constant lightning from charged dust storms, and the eerie electromagnetic phenomena would create visual effects that could easily be misinterpreted as planetary conflagration. The scientific community would find itself in the awkward position of trying to explain that Mars hasn't actually ignited, while simultaneously acknowledging that the planet has indeed become temporarily uninhabitable for human exploration. The distinction between chemically burning and electromagnetically chaotic would be lost on a public already primed by decades of disaster movies to expect the worst possible interpretations of cosmic events. International space law provides little guidance for managing electromagnetic catastrophes that cross planetary boundaries. If Atlas's effects disrupt not just Mars-based assets but also Earth-orbiting satellites that use Mars as a communication relay, questions of liability and response coordination could create diplomatic complications that persist long after the electromagnetic storms subside. The timeline for recovery from such electromagnetic chaos could span years. Unlike mechanical damage, which can sometimes be repaired through remote commands or backup systems, electromagnetic disruption affects the fundamental physics of radio communication. Spacecraft systems that depend on precise timing, navigation, and communication protocols might require complete recalibration, assuming they survive the electromagnetic assault at all. Yet even as we contemplate these electromagnetic nightmares, we must acknowledge that Mars's atmospheric chaos might not represent the worst-case scenario. What if Atlas brings something to Mars that's far more persistent than electromagnetic storms, far more dangerous than charged dust clouds? What if the real threat isn't physical or electromagnetic, but biological, contamination from another star system that could fundamentally alter not just Mars's immediate future, but humanity's long-term relationship with the red planet? The contamination scenario we're about to explore operates on timescales that make electromagnetic storms look like brief summer squalls, introducing possibilities that could complicate human Mars exploration for centuries to come. The concept of panspermia, life hitchhiking between worlds on cosmic debris, has tantalized scientists for decades, occupying a curious space between legitimate scientific hypothesis and science fiction speculation. But when that cosmic debris originates from another star system entirely, carrying chemistry forged under an alien sun, the implications become profound enough to keep astrobiologists awake at night, pondering scenarios that no earthly organism has ever faced. Atlas presents us with a disturbing possibility that no one in the scientific establishment seems eager to discuss in public forums or congressional hearings. This interstellar wanderer has spent at least 30,000 years traveling through the void between stars, its nucleus acting as a cosmic deep freeze, preserving whatever molecular cargo it might have acquired during its formation in an alien stellar system or picked up during its journey through interstellar space. The massive carbon dioxide coma that Atlas has been generating provides the perfect chemical environment for complex organic molecules, not just to survive but to evolve during interstellar transit. Carbon dioxide isn't just a simple waste gas, it's an excellent solvent for organic chemistry, capable of stabilizing complex molecular structures across the temperature and pressure ranges that Atlas has experienced during its 30,000-year journey between the stars. NASA's James Webb Space Telescope has been conducting spectroscopic analysis of Atlas's coma throughout 2025, though the results remain frustratingly locked behind layers of peer review and institutional analysis. What has been released publicly confirms the presence of carbon dioxide, water vapor, and what mission scientists diplomatically describe as complex organic species, but the true nature of these organic components remains hidden behind technical jargon that could take months to penetrate with complete scientific analysis. Meanwhile, the SphereX mission has been tracking subtle changes in Atlas's emissions that suggest something more dynamic than simple sublimation of frozen gases. The patterns detected don't match the behavior of conventional comets warming in sunlight. Instead, they hint at chemical processes that might be ongoing within the coma itself, possibly catalyzed by cosmic radiation or internal chemical reactions that have been proceeding slowly but steadily during the object's interstellar voyage. Planetary protection protocols exist specifically to prevent cross-contamination between worlds, but these procedures were designed for spacecraft traveling between planets within our solar system. No one has seriously considered what happens when an entire alien ecosystem, or at least alien chemistry, arrives at Mars without any sterilization procedures whatsoever. The October 3rd encounter could deliver organic molecules to Mars that have never existed on any planet in our solar system. These compounds, evolved under the chemical conditions of an alien stellar environment, might interact with Martian soil and atmosphere in ways that our models simply cannot predict. They might catalyze reactions that alter the planet's chemical balance in subtle but persistent ways. They might introduce molecular templates that could interfere with future searches for indigenous Martian life, creating false positives or masking genuine biological signatures with chemical noise from an interstellar visitor. Consider the nightmare scenario that keeps planetary protection specialists reaching for their emergency contact lists. Exotic, organic molecules from Atlas integrate with Mars's regolith and begin self-organizing into structures that mimic biological processes. These wouldn't necessarily be alive in any sense we would recognize, but they might be active enough to alter local chemistry, consume available resources, and spread through environmental mechanisms like wind dispersal or groundwater infiltration. Such pseudo-biological activity could render Mars unsuitable for human habitation long before we develop the technology to establish permanent colonies there. Imagine trying to set up life support systems on a planet where the soil itself has been contaminated with self-replicating chemistry that we don't understand and can't control. The risk assessment for human missions would have to be completely rewritten, potentially adding decades to development timelines while we figure out how to operate safely in a chemically compromised environment. Even more troubling is the possibility of false positives in future life detection experiments. Mars exploration has always been driven by the tantalizing possibility that we might discover evidence of past or present life on the red planet. Sophisticated instruments currently being developed for future Mars sample return missions are designed to detect the subtle chemical signatures that might indicate biological processes. But what happens when those same instruments encounter organic molecules that originated from Atlas? How do we distinguish between indigenous Martian biochemistry and contamination from an interstellar visitor? The scientific implications could set back our understanding of Mars by decades as researchers struggle to separate local signals from cosmic noise. Every future discovery would be tainted by the question of whether we're seeing genuine Martian phenomena or artifacts introduced by an alien chemistry we don't understand. The contamination scenario becomes even more complex when we consider the potential for atmospheric distribution. If Atlas's approach triggers the kind of global dust storms we discussed earlier, any organic molecules deposited on the Martian surface could become airborne and spread across the entire planet within weeks. What might begin as localized contamination around the initial deposition sites could become a planet-wide phenomenon that affects every future landing site and exploration target. NASA's current Mars exploration timeline includes ambitious plans for human missions in the 2030s, missions that depend on the assumption that Mars represents a relatively predictable environment where life support systems can function reliably and where in-situ resource utilization can provide the water, oxygen, and even fuel needed for sustained human presence. Organic contamination from Atlas could undermine these assumptions completely. Water extraction systems might become clogged with alien organic compounds that don't respond to conventional filtration techniques. Atmospheric processes might be overwhelmed by chemical reactions they weren't designed to handle. Even the psychological impact on human crews could be devastating. Imagine being the first humans to set foot on Mars, only to discover that the planet has been fundamentally altered by contamination from an interstellar visitor, making it unclear whether you're exploring Mars or some hybrid world that no longer represents the natural evolution of a solar system planet. The timeline for understanding these effects could span decades. Unlike impact craters or electromagnetic storms, which reveal their consequences relatively quickly, chemical and biological contamination operates on much longer timescales. We might not fully understand what Atlas has done to Mars until well into the 2040s or beyond, long after current mission planners have retired and new generations of scientists have inherited the consequences of decisions made during the 2025 encounter. The scientific community faces a particularly uncomfortable dilemma in discussing these possibilities publicly. Acknowledging the contamination risk might be interpreted as fear-mongering, potentially undermining public support for Mars exploration programs that have taken decades to develop and billions of dollars to implement. But failing to acknowledge these risks could leave future missions unprepared for environmental conditions that differ dramatically from current models and assumptions. International space law provides little guidance for scenarios involving contamination from interstellar objects. The Outer Space Treaty and subsequent agreements were crafted with human-caused contamination in mind, not cosmic delivery of alien chemistry. If Atlas does contaminate Mars, there's no clear legal framework for determining responsibility, coordinating international response, or managing the scientific and economic consequences of a chemically compromised planet. The contamination scenario also raises profound questions about planetary ethics that extend beyond practical concerns about mission planning and scientific methodology. Do we have the right to continue exploring Mars if that exploration might be compromised by contamination we can't control? Should future missions be postponed until we better understand what Atlas might have delivered to the Red Planet? These aren't just technical questions, they're moral ones that could reshape humanity's approach to space exploration for generations to come. Yet even as we grapple with these biological nightmares and chemical unknowns, we must remember that Atlas operates in a realm where physics itself can become chaotic, where gravitational relationships that have remained stable for billions of years can be disrupted by cosmic encounters that unfold over mere hours. What if the October 3rd encounter doesn't just alter Mars's chemistry, but fundamentally disrupts the gravitational relationships that have kept the Martian system stable since the planet's formation? The orbital chaos scenario we're about to explore operates on scales that make biological contamination look almost quaint by comparison, threatening not just the chemical integrity of Mars but the physical stability of the entire Martian system. Phobos and Deimos, Mars's two diminutive moons, have been described by astronomers as captured asteroids, irregular chunks of rock that Mars managed to gravitationally snare at some point in its distant past. But these cosmic prisoners are hardly model inmates serving quiet sentences in stable orbits. Phobos, the larger and inner of the two moons, is already serving a death sentence, spiraling slowly inward toward an inevitable collision with Mars in approximately 50 million years. Under normal circumstances, this timeline provides plenty of breathing room for human civilization to establish itself on Mars and figure out what to do about the eventual moon crash scenario. We're talking about geological timescales that dwarf the entire history of complex life on Earth. But Atlas's approach on October 3rd introduces variables that could dramatically accelerate this cosmic execution schedule, transforming a distant future problem into an immediate crisis. The gravitational reality of Atlas's encounter presents us with an interesting paradox. At a distance of 30 million kilometers, the comet's direct gravitational influence on Phobos and Deimos would be negligible, roughly equivalent to the gravitational pull of a large building on Earth trying to influence the moon's orbit. The mathematics simply don't support scenarios where Atlas reaches out with invisible hands to grab Mars's moons and fling them into new trajectories. But chaos theory teaches us that small influences can have large consequences when systems are already near critical transitions. And Phobos, as it turns out, exists in a state of gravitational precariousness that makes it exquisitely sensitive to even minor perturbations. The moon orbits Mars at an altitude of only about 6,000 kilometers, so close that it completes 3 orbits per Martian day, racing around the planet faster than Mars rotates. This proximity places Phobos well within Mars's Roche limit, the distance at which tidal forces from the planet overcome the moon's own gravity. The only thing keeping Phobos from disintegrating immediately is the internal strength of its rocky structure. And even that is gradually giving way to relentless tidal stresses that are literally pulling the moon apart, grain by grain, orbit by orbit. Recent observations have revealed that Phobos is already showing stress fractures, parallel grooves that may represent the early stages of tidal breakup. The moon is being subjected to a cosmic death by 1,000 cuts that has been proceeding for millions of years. It's a process that operates on timescales so vast that it seems almost abstract, until you introduce variables like Atlas that can push marginally stable systems over the edge into catastrophic change. Now introduce Atlas into this delicate gravitational ballet. The comet might not exert enough direct gravitational influence to matter, but it brings something potentially more dangerous: debris. As Atlas sweeps through Mars's gravitational neighborhood, it could shed material that intersects with the orbital planes of the Martian moons. Even tiny particles, when they're traveling at interstellar velocities, carry tremendous kinetic energy. A grain of sand from Atlas's coma, striking Phobos at 20 kilometers per second, would impact with the force of a small explosive device. Multiply this by thousands or even millions of particles, and you begin to understand how a seemingly gentle cosmic encounter could become a devastating bombardment. The cumulative effect of such impacts might be enough to push Phobos's already stressed structure beyond its breaking point. Instead of gradually disintegrating over millions of years, the moon could fragment catastrophically during or shortly after Atlas's passage. What has been a slow-motion cosmic demolition project could become a sudden explosion of debris. But let's escalate this scenario to its logical extreme. What if Atlas doesn't just accelerate Phobos's demise, but creates something entirely new in the annals of planetary science? What if the encounter generates enough debris to create Mars's first ring system? The physics of planetary rings are more complex than most people realize. Saturn's elegant ring system represents a delicate balance between gravitational forces, particle collisions, and electromagnetic effects that took millions of years to achieve stability. A ring system created by the violent fragmentation of Phobos would be nothing like Saturn's orderly bands of ice and rock. Instead, Mars would find itself surrounded by a chaotic cloud of debris following wildly elliptical orbits. Some fragments would be large enough to pose serious hazards to spacecraft operations, city block-sized chunks of former moon careening through Mars orbit on unpredictable trajectories. Others would be small enough to create a persistent micrometeoroid environment that could sandblast solar panels and optical instruments over time. The navigation challenges for future Mars missions would become nightmarish. Instead of planning trajectories around 2 small, predictable moons, mission planners would have to contend with thousands of fragments following unpredictable paths. The risk of collision would increase exponentially, potentially making Mars orbit too dangerous for routine spacecraft operations. We could witness the birth of humanity's first artificially created space debris field around another planet. But orbital mechanics has a cruel sense of humor when it comes to cleanup operations. Unlike terrestrial pollution, which can sometimes be remediated through human intervention, orbital debris follows the immutable laws of physics. Every collision between fragments creates more fragments, each following its own trajectory. The process feeds on itself, creating cascade effects that can persist for centuries. This is known in space operations circles as the Kessler syndrome, a runaway chain reaction of orbital collisions that renders entire regions of space unusable for practical operations. We've been worried about this phenomenon affecting Earth's orbital environment for decades, but Mars, with its weaker gravitational field and thinner atmosphere, might be even more vulnerable to such cascading destruction. The psychological impact on humanity's Mars colonization dreams would be profound and immediate. For decades, we've envisioned Mars as our backup planet, our second chance at building a sustainable civilization beyond Earth. To watch that future literally fragment before our eyes would be like witnessing the destruction of humanity's most cherished hopes for expansion beyond our home world. The timeline for recovery could span geological ages. Unlike atmospheric storms or even chemical contamination, orbital debris operates according to the slow but inexorable laws of celestial mechanics. Fragments from Phobos's destruction could continue posing hazards to Mars operations for thousands or even millions of years. Future human settlers might inherit a Mars system where the very act of reaching the planet requires navigating through a debris field created by a cosmic accident that occurred generations before their birth. The economic implications would be staggering. Mars missions are already expensive enough when dealing with predictable orbital mechanics and well-understood environmental hazards. Adding the complexity of debris field navigation would multiply costs exponentially while reducing mission success rates. Insurance companies would either refuse to cover Mars operations entirely or charge premiums that make most missions economically impossible. International space law would face unprecedented challenges in managing a debris field that affects all future Mars exploration. Current treaties assume that space debris results from human activities that can be regulated and potentially remediated. But debris from cosmic encounters falls into a legal grey area, where questions of liability and management responsibility have no clear answers. The scientific community would face its own crisis of confidence. The models and assumptions that guide space mission planning were developed under the premise that planetary systems remain relatively stable over human timescales. Atlas's potential for creating orbital chaos would force a fundamental reassessment of how we approach space exploration in a universe that proves more dynamic and unpredictable than our brief technological civilization has yet experienced. Yet even this scenario of gravitational chaos and orbital debris may not represent the ultimate worst-case outcome of Atlas's encounter with Mars. What if we're thinking too locally about the comet's potential for destruction? What if the October 3rd encounter at Mars represents not an endpoint, but merely the first domino in a cascade of gravitational interactions that could ultimately threaten Earth itself? The physics of orbital perturbations operate on timescales that make human planning horizons seem laughably short. A small gravitational nudge today might not manifest as a significant threat until decades or even centuries in the future. As we prepare to explore this chain reaction scenario, we must confront the disturbing possibility that Atlas's brief dance with Mars could set in motion a sequence of events that ultimately brings cosmic disaster to our own doorstep. Distance, in cosmic terms, provides only the illusion of safety. NASA's current projections place Atlas at its closest approach to Earth sometime in December 2025 at approximately 1.8 astronomical units, roughly 270 million kilometers away. By any reasonable measure, this represents a comfortable margin that should preclude any direct threat to our home planet. But the solar system operates as an interconnected web of gravitational influences, where the butterfly effect can manifest on planetary scales over extended timelines. What happens at Mars in October doesn't stay at Mars. It propagates outward through the complex gravitational relationships that bind our solar system together, creating ripple effects that can take decades or even centuries to fully manifest. Every gravitational encounter, no matter how minor, slightly alters the trajectory of every object involved. These changes, measured in mere meters per second, seem utterly insignificant in the context of planetary velocities measured in kilometers per second. But those tiny changes accumulate over time through a process known as gravitational resonance. Just as a small push applied at the right moment can set a massive pendulum swinging, Small orbital changes can compound over multiple passes through resonant regions of the solar system. What begins as an imperceptible nudge can eventually grow into trajectory changes, measured in thousands of kilometers, enough to transform a harmless near-miss into a civilization-ending impact. The most immediate concern involves debris. If Atlas undergoes the kind of fragmentation event we explored in our Mars impact scenario, the resulting fragments won't simply disappear after their encounter with the red planet. Each piece will continue following its own modified orbit through the inner solar system, creating what astronomers euphemistically call a persistent hazard environment. Some of these fragments might find themselves in orbital resonances with Earth's orbit, creating periodic encounters that could persist for decades. Others might be perturbed into highly elliptical paths that bring them into the inner solar system during unpredictable time windows. The result would be a subtle but measurable increase in the background flux of potentially hazardous objects threatening Earth, a cosmic tax levied by Atlas's passage that our planet would continue paying for generations. NASA's planetary defense infrastructure has made remarkable progress in recent years. The Asteroid Terrestrial Impact, Last Alert System, PAN-STARRS, and the Future Legacy Survey of Space and Time are designed to provide years or even decades of advanced warning for most objects, large enough to cause regional or global damage on Earth. But these systems were calibrated to detect objects following relatively predictable orbits within our solar system. Atlas fragments arriving on chaotic trajectories influenced by interstellar velocities and multiple gravitational encounters might not fit the standard detection profiles. Their approach angles could be unusual, their velocities unexpected, their compositions different enough from typical asteroids to confuse automated classification systems. We could find ourselves facing threats that slip through detection networks designed for more conventional cosmic hazards. The timeline for these threats could span generations, creating a particularly insidious form of cosmic risk. Unlike the immediate drama of an impact or atmospheric disruption, gravitational perturbations operate on what physicists call secular timescales, changes that accumulate slowly but inexorably over periods measured in decades or centuries. We might not fully understand the consequences of Atlas's October 3rd encounter with Mars until the 2040s or beyond. This temporal displacement of consequences creates a moral hazard that extends beyond simple risk assessment. The politicians and space agency administrators making decisions about planetary defense funding today might not be around to face the consequences of their choices when Atlas-derived fragments begin threatening Earth in the 2050s or beyond. Democratic institutions, optimized for election cycles measured in years, prove poorly suited for managing threats that operate on cosmic timescales measured in decades. The Yarkovsky effect compounds these concerns in ways that make long-term prediction nearly impossible. This subtle phenomenon occurs when small objects absorb sunlight during the day and re-radiate that heat during the night, creating a tiny but persistent thrust that can significantly alter orbits over extended periods. For fragments of Atlas that might be composed of exotic interstellar materials with thermal properties unlike anything in our solar system, the Yarkovsky effect could produce orbital evolution that defies all current models. Picture this nightmare scenario unfolding over the next 50 years. Atlas fragments, initially deemed harmless by computer simulations based on conventional asteroid behavior, gradually migrate into Earth-threatening orbits through Yarkovsky drift patterns that no one anticipated. By the time ground-based telescopes detect the threat, there might be insufficient time to organize effective deflection missions. The infrastructure for planetary defense that seems adequate for known threat categories could prove useless against hazards that don't follow the rules. The precedent for such cascading gravitational disasters already exists in our solar system's history. The Late Heavy Bombardment, which occurred approximately 4 billion years ago, may have been triggered by gravitational resonances that destabilized the outer planet's orbits, sending a barrage of comets and asteroids into the inner solar system. The craters on our moon serve as permanent reminders that gravitational chaos can transform peaceful cosmic neighborhoods into shooting galleries. But Atlas introduces variables that the Late Heavy Bombardment never included: interstellar velocities, exotic compositions, and fragmentation patterns that might not follow the rules established by billions of years of solar system evolution. We're potentially facing a new category of gravitational cascade, one for which our solar system has no historical precedent, and our models have no reliable foundation. The meteor shower implications alone could be spectacular in the most ominous sense of that word. Earth regularly encounters debris streams from known comets, producing predictable annual meteor showers that delight amateur astronomers and generally pose no threat beyond the occasional satellite impact. But meteor showers from Atlas fragments would be fundamentally different beasts entirely. These wouldn't be the gentle light shows of the Perseids or Geminids, where tiny particles burn up harmlessly in Earth's atmosphere. Atlas fragments, traveling at interstellar velocities and potentially composed of materials that don't behave like conventional meteoroids, could produce airburst events that rival the Tunguska explosion of 1908. The Tunguska event, which flattened 2,000 square kilometers of Siberian forest, resulted from an object estimated to be only 30 to 60 meters in diameter. Now imagine multiple Tunguska-class events occurring as Earth passes through debris streams from Atlas fragmentation. The cumulative effect could devastate entire continents over periods of decades. Modern civilization's vulnerability to such events has increased exponentially since 1908. Our power grids, communication networks and transportation systems create cascade failure points that didn't exist during the Tunguska era. A single airburst event over a major metropolitan area could trigger economic and social disruptions that persist for years. The insurance industry has already begun grappling with the implications of increased cosmic risk. Lloyd's of London and other major insurers have been quietly developing models for space weather events that could affect global commerce, but their current risk assessments assume that potentially hazardous objects will be detected years in advance, allowing for orderly evacuations and infrastructure hardening. Atlas fragments following chaotic, unpredictable orbits could arrive with much shorter warning times, potentially catching both emergency management systems and insurance markets completely unprepared. The result could be economic disruption that dwarfs the immediate physical damage, creating what risk analysts call a systemic cascade, where failures in one sector trigger breakdowns across multiple interconnected systems. Perhaps most unsettling is the possibility that we're already committed to this future cascade, regardless of what actually happens on October 3rd. The gravitational perturbations that will ultimately determine Atlas's long-term influence on inner solar system dynamics may have already been set in motion by earlier phases of the comet's approach. Orbital mechanics operates according to deterministic chaos, systems where tiny initial differences can produce dramatically different outcomes, but where those outcomes are nevertheless inevitable once the initial conditions are established. We may be living through the early stages of a gravitational cascade that was predetermined when Atlas first entered our solar system months ago. The monitoring systems that might provide early warning of developing threats face their own vulnerabilities in an era of increasing cosmic chaos. Ground-based telescopes can be affected by atmospheric conditions. Space-based observatories can be damaged by the same debris fields they're designed to detect. Communication systems that relay threat assessments to planetary defense networks could be disrupted by the electromagnetic chaos we explored in our Mars atmospheric scenario. But even if our detection systems function flawlessly, even if we spot every Atlas fragment decades before it threatens Earth, we face the sobering reality that deflection technology remains largely theoretical. The DART mission successfully demonstrated that we can alter an asteroid's trajectory, but only under carefully controlled conditions involving a known target with predictable composition and orbital characteristics. Atlas fragments, with their exotic interstellar origins and chaotic post-fragmentation orbits, might not respond to deflection attempts in the ways our models predict. We could find ourselves in the position of knowing exactly when and where a cosmic catastrophe will occur, but being powerless to prevent it. This is the true horror of the chain reaction scenario, not the immediate spectacle of planetary destruction, but the slow-motion catastrophe of watching our cosmic neighborhood become increasingly hazardous over timescales that exceed human political and economic planning horizons. We might be witnessing the beginning of humanity's first self-inflicted cosmic crisis, triggered by our own expansion into a solar system that was never as stable as we assumed. Yet even as we contemplate these terrestrial nightmares, we must acknowledge that our robotic emissaries currently orbiting Mars face more immediate existential threats that could unfold within hours of Atlas's October 3rd encounter. Space, despite its romantic portrayal in science fiction, remains fundamentally hostile to the delicate electronic systems that extend human presence beyond Earth's protective embrace. Our spacecraft represent triumphs of engineering precision, Complex assemblages of sensors, processors, and communication systems that must function flawlessly in environments where the smallest failure can mean mission death and the loss of billions of dollars in investment and decades of scientific work. Mars orbit presents unique challenges that push spacecraft design to its absolute limits. The radiation environment, while less intense than Jupiter's murderous magnetic field, still degrades electronic components over time through cumulative damage that eventually renders even the most robust systems unreliable. Micrometeoroid impacts, though infrequent, can disable critical systems with surgical precision, taking out specific components while leaving others untouched. Temperature extremes cycle between the frigid cold of Martian shadow and the intense heat of unfiltered sunlight, causing thermal stresses that gradually fatigue even the most robust materials. But the engineers who designed our current Mars fleet, the Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, never anticipated having to operate in the chaotic environment that Atlas's passage might create. These spacecraft were built to study Mars under normal conditions, not to survive cosmic catastrophes that could transform the entire Martian system into an electromagnetic war zone. Consider the vulnerabilities inherent in modern spacecraft architecture. High-voltage power systems, essential for operating sophisticated instruments across the vast distances of interplanetary space, become liabilities when exposed to the kind of electromagnetic chaos that Atlas could generate. Static electricity buildup from charged particle bombardment can create voltage differentials that arc across circuit boards, instantly destroying components that took years to design and test. The Mars Reconnaissance Orbiter, launched in 2005, carries some of the most sophisticated imaging and communication equipment ever deployed in Mars orbit. Its high-rise camera can resolve features smaller than a meter across on the Martian surface, while its radio science experiments probe the planet's atmospheric structure with unprecedented precision. But this technological marvel depends on star trackers, optical sensors that maintain spacecraft orientation by observing known stellar positions. A debris field from Atlas fragmentation could render these star trackers useless by creating false targets or overwhelming their sensitive photodetectors with unexpected light sources. Without reliable attitude control, the Mars Reconnaissance Orbiter's high-gain antenna couldn't maintain its precise pointing toward Earth, severing the communication link that allows the spacecraft to transmit its scientific discoveries back to mission control. MAVEN, the Mars Atmosphere and Volatile Evolution mission, faces different but equally severe challenges. This spacecraft was specifically designed to study how solar-wind interactions strip away Mars's upper atmosphere, using particle detectors and magnetometers calibrated to measure the gentle, predictable flow of charged particles from our Sun. But Atlas's passage could flood MAVEN's sensors with particle fluxes, orders of magnitude higher than anything they were designed to handle. It would be like trying to measure a gentle breeze with an instrument suddenly exposed to a hurricane. MAVEN's delicate sensors could be permanently damaged or saturated beyond their ability to provide meaningful data. The electromagnetic pulse effects, while not equivalent to the fictional EMP weapons of Hollywood thrillers, could still induce damaging currents in spacecraft wiring systems that create efficient antennas for capturing electromagnetic energy from external sources. Each spacecraft also carries its own unique vulnerabilities based on mission-specific design choices. Mars Express, the European Space Agency's veteran Mars explorer, has been operating since 2004 and shows signs of age in several subsystems. Components that were already operating near their design limits might not survive additional stresses from an unexpectedly chaotic electromagnetic environment. The Trace Gas Orbiter represents our most recent addition to the Mars fleet, equipped with state-of-the-art spectrometers designed to detect trace gases in the Martian atmosphere, including potential biosignatures that could indicate past or present life. But these ultra-sensitive instruments require extraordinarily stable operating conditions to distinguish genuine atmospheric signals from instrumental noise. The chaotic electromagnetic environment created by Atlas's passage could overwhelm these sensitive measurements with false signals, rendering months or even years of observations scientifically worthless. Even worse, electromagnetic interference could damage the spectrometer's calibration systems, requiring complex recalibration procedures that might not be possible to execute remotely. The instruments that represent our best hope for detecting life on Mars could become useless at precisely the moment when Atlas's passage might be delivering exotic organic chemistry that could confuse or contaminate future life detection efforts. But let's escalate this scenario to its most catastrophic logical conclusion. What if Atlas's passage doesn't just threaten individual spacecraft, but creates systemic failures across the entire Mars orbital infrastructure? What if the electromagnetic chaos proves severe enough to trigger a cascade of safe mode shutdowns that effectively blinds humanity's robotic presence at Mars? Spacecraft designers incorporate safe mode systems as a last resort for preserving mission capability when sensors detect anomalous conditions that could threaten spacecraft survival. In safe mode, all non-essential systems shut down, solar panels orient toward the sun for maximum power generation, and the spacecraft waits for commands from Earth to assess damage and attempt recovery procedures. But safe mode assumes that anomalous conditions are temporary and that ground controllers will eventually be able to re-establish communication to begin recovery procedures. If Atlas creates electromagnetic chaos that persists for weeks or months, our Mars orbiters could find themselves trapped in safe mode for extended periods, unable to conduct science operations or even relay communications from surface rovers. The psychological impact on Mars exploration programs would be devastating. Imagine the public reaction to news that all of our Mars orbiters have gone silent simultaneously. Social media would explode with conspiracy theories about cosmic catastrophes and government cover-ups. The carefully cultivated public support for Mars exploration, built up over decades of successful missions and stunning imagery, could evaporate overnight as people begin to question whether space exploration is worth the risks and costs. Mission controllers at JPL and other space agencies would face an unprecedented crisis management challenge. Standard spacecraft recovery procedures assume that you can communicate with the affected vehicle to diagnose problems and upload corrective commands. But if electromagnetic interference prevents reliable communication, ground controllers might find themselves essentially helpless to assist their distant robotic charges. The ripple effects would extend to Mars surface operations as well. The Perseverance and Curiosity rovers depend on orbital relay assets to maintain regular communication with Earth. Without these relay systems, the rovers would be forced to communicate directly with Earth using their own lower power radio systems, a process that severely limits data transmission rates and operational flexibility. Even more troubling is the possibility that Atlas could trigger the kind of rare space weather coupling event that space physicists have been warning about for decades. If the comet's passage coincides with a major solar energetic particle event or coronal mass ejection, the combined effects could overwhelm spacecraft shielding systems that were designed to handle either threat individually but not both simultaneously. The recovery timeline for such cascading failure could span years. Unlike terrestrial infrastructure, which can be repaired by sending technicians to the affected location, spacecraft failures in Mars orbit require complex troubleshooting procedures conducted across interplanetary distances with communication delays measured in minutes. Some spacecraft might never recover from the electromagnetic trauma of Atlas's passage. Components damaged by electrical surges or degraded by prolonged exposure to charged particle bombardment might simply fail to respond to recovery attempts. Missions that have successfully operated for decades could end abruptly, not from the gradual aging of their systems, but from sudden exposure to cosmic forces that overwhelm their design parameters. The loss of Mars orbital assets would set back our understanding of the red planet by years or possibly decades. Scientific investigations that depend on long-term monitoring would be interrupted, just as they were beginning to reveal crucial insights about Martian climate evolution, atmospheric chemistry, and geological processes. But perhaps most ominously, the failure of our Mars spacecraft fleet would leave us blind to whatever Atlas actually does to the red planet itself. We might find ourselves in the position of knowing that something significant happened at Mars on October 3rd, but being unable to observe or understand the consequences until new missions can be designed, built, and launched. A process that typically requires at least a decade. Yet even as we contemplate these technological nightmares, we must remember that Atlas operates in the realm of solar system dynamics, where even our sun can be influenced by sufficiently dramatic cosmic events. What if the October 3rd encounter represents not just a threat to Mars and its artificial satellites, but the beginning of a solar weather catastrophe that could affect every planet in our cosmic neighborhood? The sun, for all its apparent constancy as it rises and sets with reassuring predictability, operates as a barely controlled fusion reactor, balanced on the knife's edge between stellar stability and explosive chaos. Solar activity follows 11-year cycles that can unleash electromagnetic storms capable of disrupting technology across the entire solar system. But these natural solar tantrums pale in comparison to what might happen if Atlas's passage through the inner solar system coincides with peak solar activity, creating a perfect storm of cosmic conditions that could transform our life-giving star into an instrument of planetary destruction. Atlas's perihelion, its closest approach to our Sun, occurs in late October 2025 at approximately 1.4 astronomical units from our star. While this distance keeps the comet safely outside the realm of the dramatic sun grazers that occasionally plunge directly into our star's corona, it places Atlas well within the region where solar-wind interactions can become intense and unpredictable, creating conditions that could trigger cascading effects throughout the solar system. The physics of comet solar-wind interaction follow established principles under normal circumstances. As a comet approaches the Sun, solar radiation vaporizes its surface materials, creating the characteristic coma and tail that make these objects visible from Earth. The solar wind, a stream of charged particles flowing outward from the Sun at speeds exceeding 400 kilometers per second, shapes these emissions into the distinctive anti-sun pointing tails that have inspired human imagination for millennia. But Atlas isn't a normal comet operating under normal circumstances. Its massive carbon dioxide coma and erratic brightness variations suggest internal processes that don't match our standard models of cometary behavior. When an object following non-standard patterns encounters the complex electromagnetic environment near the Sun, the results can be genuinely unpredictable, potentially triggering solar responses that fall outside the range of natural variation. Consider what happens when Atlas's ion tail, a stream of electrically charged particles accelerated by the solar wind, extends millions of kilometers into space during the comet's perihelion passage. This tail doesn't exist in isolation. It interacts with the solar wind, with the Sun's magnetic field, and potentially with other electromagnetic phenomena in ways that could create feedback loops affecting solar activity itself. The Sun's magnetic field lines extend throughout the solar system in complex patterns that astronomers are still trying to fully understand. When a massive ion stream from Atlas intersects these field lines, it could theoretically create perturbations that propagate back toward the Sun, potentially triggering enhanced solar activity in regions that might otherwise remain quiet. The electromagnetic perturbations from the comet's ion tail could serve as a trigger mechanism for solar flares or coronal mass ejections that wouldn't have occurred under normal conditions. Now let's escalate this scenario to its most alarming possible conclusion. What if Atlas's perihelion passage occurs during a period when the Sun is already approaching peak activity in its natural cycle? What if the electromagnetic perturbations from the comet's ion tail arrive at our star just as solar magnetic field lines are becoming unstable and primed for explosive release? The result could be a solar energetic particle event of unprecedented magnitude, a cosmic storm that makes the Carrington event of 1859 look like a gentle spring shower. The Carrington event, caused by a relatively modest coronal mass ejection, was powerful enough to disrupt telegraph systems across North America and Europe, creating auroras visible as far south as the Caribbean. But that 19th century solar storm occurred during an era when human civilization had minimal dependence on electrical infrastructure. A Carrington-class event today would devastate power grids, satellite networks, and communication systems across multiple continents. The economic damage would be measured in trillions of dollars, and the recovery time could span years as industrial civilization struggles to rebuild infrastructure designed under the assumption that space weather represents a manageable risk rather than an existential threat. An Atlas-enhanced solar storm could be orders of magnitude more severe. The charged particles accelerated by such an event would arrive at Earth traveling at significant fractions of the speed of light, carrying energies that would overwhelm even hardened satellite systems and potentially damage components of terrestrial power grids despite their protective shielding. The space weather monitoring systems that provide advanced warning of solar storms, SOHO, the Geostationary Operational Environmental Satellites, and the Deep Space Climate Observatory would themselves be at risk from the very phenomena they're designed to detect. If these early warning systems are damaged or destroyed by the initial wave of comet-charged particles, subsequent waves could arrive at Earth with little or no advanced notice. The cascade effects on modern civilization would be catastrophic beyond anything in human experience. GPS navigation systems would fail, as satellites lose their ability to maintain precise timing. The internet backbone, dependent on precisely synchronized data transmission protocols, would fragment as timing references disappear. Air traffic control systems would revert to visual flight rules as radar systems succumb to electromagnetic interference. But Earth wouldn't be the only planet affected by such a solar catastrophe. Mars, already facing potential chaos from Atlas's direct passage, would find itself bombarded by charged particles, energetic enough to strip away significant portions of its already tenuous atmosphere. The radiation levels at the Martian surface would spike to levels that would be immediately lethal to any human explorers, unfortunate enough to be present during such an event. The moons of Jupiter and Saturn, normally protected from the worst solar storms by their planet's powerful magnetic fields, could experience radiation doses that sterilize their surfaces to depths measured in meters. Europa and Enceladus, prime targets in the search for extraterrestrial life, might find their subsurface oceans bombarded with enough radiation to destroy any biological processes that might have been occurring there. Perhaps most disturbing is the possibility that an Atlas-triggered solar storm could create a feedback loop that persists long after the comet has departed the inner solar system. Solar magnetic field disruptions can take months or even years to fully stabilize, during which time our star could continue producing enhanced particle emissions that threaten technological civilization across multiple planets. The historical record provides little guidance for managing such a scenario because no similar event has occurred during the era of space-age technology. The best solar storm data we have comes from ice core analyses and tree ring studies that suggest periodic episodes of enhanced solar activity throughout Earth's history. But these natural archives tell us nothing about the specific mechanisms or timelines involved in comet-triggered solar enhancement. Space weather prediction models, sophisticated as they are, weren't designed to account for the additional variables introduced by interstellar comets interacting with solar magnetic fields. The computer simulations that space weather forecasters rely on might prove completely inadequate for predicting the behavior of an Atlas-enhanced solar storm, leaving emergency management systems and infrastructure protection efforts operating essentially blind. The policy implications alone would be staggering. How do you prepare modern technological civilization for a phenomenon that might occur with little warning and could persist for months? How do you maintain emergency services when the communication systems they depend on might be the first casualties of electromagnetic chaos? How do you prevent social collapse when the just-in-time supply chains that feed modern cities depend on GPS navigation and electronic payment systems that could fail simultaneously? International cooperation, already strained by terrestrial political conflicts, would be essential for managing a global space weather catastrophe. But the same electromagnetic chaos that threatens technological systems could also disrupt the communication networks that international coordination depends on. We might find ourselves facing a planetary emergency while simultaneously losing the ability to coordinate our response efforts effectively. Yet even as we contemplate these electromagnetic nightmares and solar catastrophes, we must remember that Atlas might be delivering more than just charged particles and magnetic field disruptions to the inner solar system. What if the comet's passage doesn't just threaten our technology, but fundamentally alters the chemical environment of planets in ways that could affect their long-term habitability? What if Atlas's true legacy isn't measured in immediate destruction, but in subtle chemical changes that accumulate over decades, transforming worlds in ways we're only beginning to understand? The concept of terraforming Mars, transforming the red planet into a world suitable for human habitation, has captivated scientists and science fiction writers for decades. Most proposals involve gradual, carefully controlled processes spanning centuries, releasing greenhouse gases to thicken the atmosphere, melting polar ice caps to create bodies of liquid water, introducing extremophile organisms to begin establishing biological cycles. These are dreams of patient engineering, of humanity slowly coaxing Mars into becoming a second Earth through methodical application of planetary science and biotechnology. But what if Atlas accomplishes a form of terraforming through cosmic accident? Not the gradual, beneficial transformation we've envisioned in countless scientific papers and speculative fiction, but a rapid, chaotic alteration that makes Mars even less hospitable to human life than it already is. What if October 3rd marks not just a close encounter, but the beginning of an inadvertent geoengineering project that transforms Mars into something unprecedented in our solar system? The massive carbon dioxide emissions from Atlas's Comet represent a chemical payload of staggering proportions. Spectroscopic analysis suggests that the comet is venting CO2 at rates that dwarf anything previously observed in our solar system. While most of this material will miss Mars entirely and continue into interplanetary space, even a small fraction could represent millions of tons of additional greenhouse gases entering the Martian system. Under normal circumstances, this might sound beneficial for terraforming efforts. Carbon dioxide, after all, is the primary greenhouse gas that most Mars terraforming proposals plan to introduce to thicken the planet's atmosphere and raise surface temperatures. Additional CO2 from Atlas might seem like a head start on humanity's eventual climate engineering projects, a cosmic gift that jumpstarts the atmospheric thickening process by centuries, but the devil as always lurks in the details of planetary atmospheric chemistry. Mars's current atmospheric system exists in a delicate equilibrium that has persisted for millions of years. Sudden chemical inputs, even of gases that already exist in the atmosphere, can trigger cascading reactions that destabilize established patterns in unpredictable ways. Atlas's carbon dioxide isn't arriving through the gradual, controlled processes that terraforming engineers envision. Instead, it's being delivered as a chaotic surge, coinciding with electromagnetic disruptions, possible debris impacts, and dust storm activity that could fundamentally alter how the gas interacts with existing atmospheric chemistry. The timing and delivery mechanism matter as much as the chemical composition. It's the difference between carefully seasoning a soup and dumping an entire container of salt into a delicate recipe. Consider the albedo effects alone. Mars's reddish surface reflects sunlight in ways that help maintain the planet's current temperature regime, creating a feedback system that has remained stable for millions of years. But Atlas's passage could deposit significant quantities of dark, organic-rich dust across large portions of the planetary surface. This dust, composed of materials that formed in an alien stellar environment, might have thermal absorption characteristics completely unlike anything currently on Mars. Dark surfaces absorb more heat than light surfaces, a basic physical principle that could trigger runaway heating in regions where Atlas dust accumulates. Local temperature spikes could vaporize subsurface water ice, adding water vapor to an atmosphere that's already struggling to maintain chemical equilibrium. The additional moisture could interact with Atlas's carbon dioxide in ways that create acid rain conditions, further altering surface chemistry in a cascade of unintended consequences. But here's where the scenario becomes genuinely nightmarish from a terraforming perspective. What if Atlas's chemical contributions don't make Mars more Earth-like, but instead push the planet toward a Venus-like greenhouse catastrophe? Venus, despite being similar to Earth in size and composition, experienced a runaway greenhouse effect that transformed it into a hell world with surface temperatures hot enough to melt lead and atmospheric pressures, crushing enough to destroy spacecraft within hours. Mars, with its lower gravity and greater distance from the Sun, shouldn't be susceptible to Venus-style greenhouse runaway under normal circumstances. But Atlas introduces variables that have never been tested in planetary climate models. Exotic organic compounds from interstellar space might catalyze chemical reactions that amplify greenhouse warming beyond what pure CO2 additions would suggest. The timeline for such changes could be measured in years rather than the geological timescales typically associated with natural climate evolution. Planetary atmospheres, when pushed beyond critical thresholds, can undergo rapid transitions that completely alter their character within decades. What begins as a modest enhancement of Mars's existing greenhouse effect could accelerate into irreversible atmospheric transformation that makes the planet uninhabitable for human colonization efforts. Future Mars missions, planned under the assumption that the planet's environment will remain relatively stable and predictable, could find themselves operating in conditions that bear no resemblance to current models. Life support systems designed for Mars's current atmospheric composition might fail catastrophically when confronted with the altered chemistry that Atlas leaves behind. In situ resource utilization, the cornerstone technology that makes long-term Mars habitation economically feasible, depends on being able to extract water, oxygen, and even rocket fuel from the Martian environment using known chemical processes. But if Atlas fundamentally alters the planet's chemical inventory, these SOU systems might become useless or even dangerous to operate. Imagine astronauts arriving at Mars in the 2030 SOUs only to discover that their atmospheric processes can't function in the chemically altered environment that Atlas created. Instead of producing breathable air, the systems might generate toxic compounds that could poison entire habitats. Water extraction systems might encounter organic contaminants that render the recovered water unsafe for human consumption despite sophisticated purification efforts. The psychological impact on humanity's space colonization dreams would be devastating and immediate. Mars represents our nearest feasible backup planet, our insurance policy against existential risks that could threaten Earth-based civilization. To discover that an interstellar visitor has rendered Mars uninhabitable just as we're developing the technology to establish permanent settlements, there would be like watching our species' long-term survival prospects evaporate in real time. But the changes Atlas brings to Mars might not be limited to atmospheric and surface chemistry. The comet's passage could alter the planet's electromagnetic environment in ways that affect everything from aurora displays to the behavior of dust storms. Mars's weak magnetic field provides minimal protection against charged particles, making the planet exquisitely sensitive to changes in the local space weather environment. Enhanced electromagnetic activity could affect the Martian ionosphere in ways that interfere with radio communications for decades. Future Mars missions might find themselves operating in a communications environment that requires completely different technologies from those currently being developed. The reliable communication windows that mission planners take for granted might become sporadic and unpredictable, forcing a complete rethink of how we maintain contact with human settlements on Mars. The dust storm implications alone could reshape Mars exploration strategies for generations. If Atlas's electromagnetic effects make global dust storms more frequent or more intense, the reliable solar power that most Mars missions depend on could become unreliable. Nuclear power sources, currently viewed as optional for Mars missions, might become essential for any long-term operations in a world where dust storms never end, and solar energy becomes unpredictable. Perhaps most unsettling is the possibility that we won't fully understand Atlas's impact on Mars until decades after the October 3rd encounter. Atmospheric chemistry operates on timescales that can make immediate assessment impossible. Chemical reactions initiated by Atlas's passage might continue occurring for years, gradually altering Mars's environment in ways that won't become apparent until future missions attempt to operate in the changed conditions. The terraforming disaster scenario forces us to confront an uncomfortable truth about planetary engineering. We don't understand planetary atmospheres well enough to predict how they'll respond to sudden large-scale chemical inputs. Our models work reasonably well for gradual changes occurring over geological timescales, but they've never been tested against the kind of cosmic chemical shock that Atlas might deliver. We're essentially conducting a massive, uncontrolled experiment on the planet we hope to colonize, using an interstellar visitor as our inadvertent laboratory assistant. The results of this experiment might not be known for decades, but they could determine whether Mars remains a viable destination for human expansion, or becomes a cautionary tale about the unintended consequences of cosmic encounters. Yet even as we contemplate these environmental nightmares and atmospheric catastrophes, we must acknowledge that the most insidious effects of Atlas's passage might not be physical at all. What if the October 3rd encounter unfolds exactly as predicted by official models, with no dramatic impacts, no electromagnetic chaos, no chemical catastrophes, but the public refuses to believe that nothing significant occurred? What if the real disaster is informational rather than physical, creating social and political chaos that proves more damaging than any cosmic catastrophe? Information in the modern age flows according to its own chaotic dynamics that can be more unpredictable than orbital mechanics, and more dangerous than cosmic radiation. When significant astronomical events occur, the gap between scientific reality and public perception can widen into chasms that swallow rational discourse entirely, creating information environments where speculation becomes indistinguishable from fact and where institutional credibility can be destroyed faster than spacecraft in a debris field. Atlas's October 3rd encounter with Mars presents a perfect storm of conditions for informational catastrophe. The event occurs during a solar conjunction period when Earth-based observations are limited, creating natural information gaps that speculation rushes to fill. The scientific data requires weeks or months of analysis before meaningful conclusions can be drawn, but social media operates on timescales measured in minutes and hours. Most critically, the encounter involves an interstellar object whose behavior doesn't match established patterns, a cosmic wildcard that feeds speculation far more readily than it provides definitive answers. NASA and the European Space Agency have been conspicuously measured in their public communications about Atlas. Official statements acknowledge the unusual nature of the object and confirm plans for observational campaigns during the Mars encounter, but they stop short of providing the kind of dramatic imagery and speculative scenarios that capture public imagination and generate viral social media content. This cautious approach, while scientifically appropriate and professionally responsible, creates an information vacuum that alternative narratives rush to fill. Social media algorithms designed to maximize engagement rather than accuracy amplify the most dramatic and alarming interpretations of incomplete data. By the time official scientific analysis is complete and peer-reviewed results are published, public opinion may be so thoroughly shaped by misinformation that factual corrections become ineffective. The precedent for astronomical misinformation campaigns offers little comfort for those hoping rational discourse will prevail. The 2021 UAP disclosures by the US government demonstrated how quickly speculation can outpace official information when dealing with phenomena that challenge conventional understanding. Congressional hearings that were intended to provide transparency instead generated more questions than answers, feeding conspiracy theories rather than resolving them. Atlas presents an even more complex challenge because the object is genuinely anomalous in ways that resist simple explanation. Its massive carbon dioxide coma, erratic brightness variations, and exotic orbital characteristics provide just enough genuine mystery to make even outlandish theories seem plausible to non-experts. The delayed release schedule for scientific data compounds the problem exponentially. The James Webb Space Telescope's infrared observations of Atlas conducted in August remain under analysis by research teams who follow peer review protocols that prioritize accuracy over speed. Preliminary results might not be publicly available until months after the October 3rd encounter, creating a prolonged period when speculation operates without factual constraints or authoritative correction. Meanwhile, amateur astronomers and citizen science groups are conducting their own observations with equipment that, while impressive for backyard use, lacks the sensitivity and calibration of professional observatory instruments. Their images and measurements, shared instantly across social media platforms, may contain artifacts or misinterpretations that professional astronomers would immediately recognize, but that appear compelling to general audiences hungry for immediate information. The "don't look up" scenario emerges when this combination of factors creates conditions where the public believes something catastrophic has occurred at Mars, regardless of what actually happened. If Atlas's encounter produces any unusual phenomena, even relatively minor events that fall well within the range of natural variation, they could be interpreted as evidence of cosmic catastrophe or institutional cover-up. Picture this nightmare timeline unfolding in real time across social media platforms. Atlas passes Mars on October 3rd with minimal fanfare, producing subtle changes in the planet's electromagnetic environment that require sophisticated analysis to detect and interpret. Mars orbiters continue functioning normally, but implement precautionary safe mode protocols that temporarily reduce science operations as a routine safety measure. Surface rovers experience brief communication interruptions, as ionospheric conditions fluctuate within normal parameters. From a scientific perspective, this represents an interesting but non-catastrophic encounter that provides valuable data about interstellar object interactions with planetary magnetospheres. The temporary reduction in data transmission creates normal operational gaps that mission planners anticipated and prepared for. But from a public information perspective, it could be interpreted as evidence of deliberate information suppression. The temporary reduction in Mars imagery transmission creates a blackout that conspiracy theorists interpret as evidence that something terrible has occurred. The technical explanations provided by space agencies, detailed discussions of ionospheric propagation effects and spacecraft operating procedures, sound like bureaucratic double talk to audiences, primed to expect dramatic revelations and immediate answers. Social media fills with increasingly elaborate theories about what really happened during the Atlas encounter. Computer-generated images purporting to show Mars impact craters circulate faster than official corrections can be issued. Amateur radio operators claim to have intercepted emergency transmissions from Mars orbiters that space agencies refuse to acknowledge. The distinction between legitimate scientific caution and suspicious institutional secrecy becomes blurred beyond recognition. The psychological dynamics that drive such information cascades are well understood by cognitive scientists, but remain poorly addressed by official communication strategies. When people are primed to expect dramatic events, normal scientific caution is interpreted as evasion. When official explanations involve technical details that require specialized knowledge to understand, they're dismissed as attempts to obscure rather than illuminate. The 2024 presidential election demonstrated how quickly misinformation can reshape public perception of reality when it confirms existing biases and fears. The same psychological mechanisms that allowed unfounded claims about election fraud to persist, despite overwhelming factual evidence, could easily be applied to claims about cosmic cover-ups and suppressed astronomical data. Congressional oversight of space agencies, intended to ensure transparency and accountability, could actually amplify misinformation if representatives without scientific training demand answers to questions that can't be answered definitively with available data. Hearings that feature dramatic testimony about potential cosmic threats could generate media coverage that treats speculation as established fact, creating a feedback loop where political pressure forces premature disclosure of preliminary results. The international dimension adds another layer of complexity to information management. The European Space Agency, with its different communication protocols and political constraints, might release information on schedules that don't align with NASA's plans. These timing differences could be interpreted as evidence of coordination failures or deliberate information management rather than routine operational considerations. Amateur astronomers in countries with different transparency traditions might share observations that contradict or complicate official narratives. Chinese or Russian space agencies, operating under different political pressures, might characterize the same events in ways that seem inconsistent with Western scientific agencies' interpretations. The cumulative effect could be a global information environment, where multiple contradictory versions of what really happened at Mars compete for public attention, with scientific accuracy becoming just one variable among many in determining which narratives gain traction. But perhaps most insidiously, the don't look up scenario could become self-fulfilling if public pressure forces premature disclosure of preliminary scientific results that later prove incorrect. Space agencies facing congressional inquiries and media scrutiny might feel compelled to release tentative findings that satisfy public demand for information, but lack the rigorous analysis needed for scientific accuracy. These premature disclosures, when later corrected by more complete analysis, could be interpreted as evidence of incompetence or deliberate deception rather than normal scientific process. The correction cycle, where initial dramatic claims are gradually moderated by more careful analysis, mirrors the pattern that fuels conspiracy theories about government cover-ups. The long-term consequences for space science could be severe and lasting. Public trust in space agencies, built up over decades of successful missions and stunning discoveries, could be damaged by information management failures during the Atlas encounter. Future missions might face skeptical audiences who've been conditioned to doubt official explanations of astronomical phenomena. Congressional funding for space exploration could suffer if legislators conclude that space agencies can't be trusted to provide accurate, timely information about cosmic events. The scientific community's relationship with social media platforms could deteriorate if researchers conclude that these systems actively undermine scientific communication rather than facilitating it. Yet even as we contemplate these informational nightmares and communication breakdowns, we must prepare for the possibility that October 3rd will pass without providing clear resolution to any of the questions. Atlas has raised, what happens when the most significant astronomical event of our generation occurs and leaves us with more mysteries than answers? What happens when the universe refuses to provide the dramatic closure that human psychology demands, and we're forced to confront the possibility that some cosmic encounters simply end with ellipses rather than exclamation points? October 3rd, 2025, the day Mars died. Not in the literal sense, of course. Planets don't die the way living creatures do. They don't take final breaths or fade peacefully into cosmic night. But on this date, Mars as we've known it, humanity's next frontier, our red-hued beacon of hope in the darkness of space, ceased to exist as a destination for human exploration, and became instead a cautionary tale about the violence that lurks in the seemingly empty spaces between worlds. The impact occurred at 1407 Universal Time as Atlas fragment designation AF7 slammed into Mars's northern hemisphere at a velocity that made bullets look sluggish. The object, roughly 400 meters in diameter, and composed of exotic ices and organic compounds that had never existed anywhere in our solar system, delivered the kinetic energy equivalent of several thousand nuclear weapons to a planet utterly unprepared for such cosmic violence. Within minutes, the Mars Reconnaissance Orbiter's cameras captured images that would haunt planetary scientists for generations, an expanding fireball that briefly outshone the sun in Mars's pale sky, followed by a shockwave that raced across the planet's surface at hypersonic speeds, obliterating everything in its path. The crater, When the dust finally settled enough for orbital reconnaissance, measured 37 kilometers across, a wound in Mars's ancient surface that exposed rock formations that hadn't seen daylight since the planet's youth. But the crater was merely the beginning of Mars's transformation into an alien world. The impact had excavated millions of tons of subsurface permafrost, instantly vaporizing water ice that had been locked in Mars's crust for billions of years. This sudden injection of water vapor into the thin Martian atmosphere created weather patterns that defied every model in the climatology textbooks. Massive storm systems, driven by temperature differentials that had never existed in Mars's recorded history, began forming within hours of the impact. The electromagnetic pulse generated by the collision overwhelmed every piece of human technology in Mars orbit simultaneously. The Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, humanity's electronic eyes at the red planet, all triggered emergency safe mode protocols as their star trackers lost lock and their communication systems were flooded with radio frequency interference from the ionized debris cloud. But safe mode protocols assume that anomalous conditions are temporary. They're designed to protect spacecraft during brief periods of uncertainty, not during planetary catastrophes that fundamentally alter the electromagnetic environment for months or years. One by one, as backup power systems depleted and critical components failed under conditions they were never designed to handle, the orbiters fell silent. The communication blackout with Mars lasted 14 months. For over a year, humanity had no direct contact with the red planet that had captivated our imagination for centuries. Perseverance, curiosity, and the international collection of landers that had been studying Mars's geology and climate vanished into radio silence. Mission controllers at JPL, normally accustomed to receiving daily reports from their robotic charges, found themselves staring at blank screens and dead communication channels. The psychological impact on Earth was immediate and profound. Mars represented humanity's next chapter, our cosmic coming-of-age story. To watch it disappear from our technological grasp was like witnessing the destruction of our species' most cherished dreams. Stock markets plunged as aerospace companies saw their Mars exploration contracts evaporate overnight. Congressional hearings demanded answers that no one could provide, while social media exploded with conspiracy theories and apocalyptic speculation. When communication was finally re-established through emergency protocols and hastily launched replacement satellites, the Mars that emerged from the radio silence bore little resemblance to the world we thought we knew. The planet's entire atmospheric circulation pattern had been disrupted by the impact. What had been a relatively predictable climate system with seasonal dust storms and well-understood weather patterns had become chaotic and unpredictable. Global dust storms, once rare events that occurred every few Martian years, became the new normal. The planet's surface remained shrouded in a persistent veil of suspended particles that blocked sunlight and made solar power unreliable for any surface operations. Temperatures plummeted as the dust-laden atmosphere reflected incoming solar radiation back into space, triggering a nuclear winter effect that persisted for over 3 Martian years. The radiation environment around Mars had been permanently altered by the impact. The collision had not only lofted radioactive materials from deep within Mars's crust, but had also created a temporary debris ring around the planet. A chaotic collection of impact ejecta that bombarded the upper atmosphere for months, creating persistent auroral displays and ionospheric disturbances that made radio communication sporadic and unreliable. Phobos, Mars's larger moon, suffered collateral damage that sealed the fate of any future human missions to Mars. Impact debris from the surface collision had struck the irregularly shaped moon with sufficient force to destabilize its already precarious orbit. Instead of the gradual 50-million-year death spiral that astronomers had predicted, Phobos began fragmenting immediately. The chunks of former moon, ranging in size from boulders to building-sized fragments, followed chaotic orbits that made navigation through Mars's orbital space a deadly game of cosmic roulette. Any spacecraft attempting to reach Mars would have to thread its way through a 3-dimensional minefield of rocky debris, moving at speeds that would turn even small collisions into catastrophic events. The dreams of Mars colonization, which had seemed tantalizingly close to reality in the early 2020s, evaporated in the radioactive dust clouds that now permanently shrouded the red planet. The carefully planned Artemis Mars missions were cancelled indefinitely. The international Mars exploration treaties became obsolete overnight as the planet they were designed to govern became too dangerous to visit. Private space companies that had invested billions in Mars transportation systems found their business models destroyed by cosmic accident. SpaceX's Starship, designed specifically for Mars cargo delivery, was hastily repurposed for lunar missions and asteroid mining operations. Blue Origin's Mars landing systems became museum pieces before they ever flew, monuments to dreams that died in a fraction of a second on a Friday afternoon in October. The scientific community struggled to comprehend the magnitude of what had been lost. Mars had been our natural laboratory for studying planetary evolution, climate change, and the possibility of life beyond Earth. The rovers and landers that had spent decades carefully analyzing Martian soil samples were now buried under meters of radioactive debris, their discoveries forever lost to the cosmic catastrophe. But perhaps the most devastating realization was temporal. The Mars that Atlas had destroyed was irreplaceable on human timescales. Planetary atmospheres can recover from major disruptions, but the process typically requires millions of years. The Mars that might eventually emerge from the chaos Atlas had created would be fundamentally different from the world that had beckoned to human explorers for generations. The impact had altered Mars's axial tilt slightly, changing the planet's seasonal patterns in ways that would take decades to fully understand. The massive injection of water vapor and exotic organic compounds from Atlas's nucleus had initiated atmospheric chemistry that followed no terrestrial models. This wasn't the gradual terraforming that scientists had envisioned. It was rapid, chaotic planetary transformation that rendered all previous Mars exploration plans obsolete. The ripple effects extended far beyond Mars itself. The destruction of humanity's most accessible stepping stone to the outer solar system forced a complete recalculation of our species' expansion into space. Instead of using Mars as a staging area for missions to the asteroid belt and the moons of Jupiter, space agencies were forced to develop more complex and expensive direct routes to these destinations. The psychological trauma of watching our cosmic neighbor become uninhabitable created a generation of space scientists who viewed interstellar objects with suspicion rather than wonder. The romantic notion of comets as harbingers of cosmic beauty was replaced by a pragmatic understanding that the universe contains forces capable of destroying worlds without notice or malice. Congressional funding for planetary defense programs increased dramatically as the reality of cosmic threats became undeniable. The DART mission's success in deflecting asteroid Didymos, once viewed as an interesting technology demonstration, suddenly became the foundation for a multi-billion-dollar planetary protection initiative designed to prevent future Atlas-scale disasters. Yet even as humanity mourned the loss of Mars as a destination, we began to understand that the October 3rd disaster might have revealed something even more troubling about our cosmic neighborhood. If Atlas could destroy Mars through a chance encounter, what other interstellar visitors might be silently approaching our solar system, carrying the potential for even greater catastrophes? The monitoring networks established to track near-Earth asteroids were hastily expanded to detect interstellar objects years before their closest approaches to populated worlds. The assumption that space was mostly empty and safe was replaced by a sobering recognition that the universe was full of wandering objects capable of altering or destroying planets on timescales far shorter than geological processes. As we contemplate this alternate history where Mars died on October 3rd, we must remember that the universe rarely provides such dramatic closure to cosmic mysteries. But the scenario forces us to confront uncomfortable questions about our cosmic vulnerability and the assumptions we make about planetary stability. What if October 3rd passes quietly, leaving us with more questions than answers about our relationship with interstellar visitors? October 3rd came and went like a cosmic whisper rather than a scream. The European Space Agency's final trajectory calculations placed Atlas at its closest approach to Mars, 30.2 million kilometers, at precisely 11:17 Universal Time. No impacts occurred. No electromagnetic storms materialized. No global dust tempests engulfed the red planet in radioactive chaos. Mars continued its ancient orbit around the Sun, apparently unperturbed by its brush with the interstellar visitor that had captivated human attention for months. The first official statement came from ESA Mission Control 6 hours after closest approach. 3I Atlas has completed its Mars encounter within all predicted parameters. Mars orbital assets report normal operations. No anomalous activity detected at this time. Further analysis pending. 42 words that somehow managed to sound both reassuring and deeply unsatisfying. Like a doctor's report that finds nothing wrong but fails to explain why you still feel terrible. Within minutes of the release, social media platforms erupted with a collective expression of anticlimax that bordered on indignation. "That's it" became the most trending phrase on Twitter within an hour. Reddit forums dedicated to Atlas speculation descended into bitter debates about whether the boring outcome represented successful scientific prediction or evidence of a coordinated cover-up designed to prevent public panic. The public reaction revealed something profound and troubling about human psychology and our relationship with cosmic events. For months, Atlas had captured global attention precisely because it represented the unknown, the potentially catastrophic, the cosmically significant. Its mysterious behavior and interstellar origins had fed speculations that ranged from scientifically plausible to utterly fantastic. But all of them shared a common assumption that something dramatic would occur when this alien visitor reached its closest approach to Mars. The reality of cosmic encounters, however, rarely matches human expectations for narrative satisfaction. The universe operates according to physical laws that are indifferent to our desire for climactic resolution, for dramatic conclusions that provide clear answers to the questions we've been asking. Most astronomical events, even genuinely significant ones, unfold in ways that seem mundane to observers who weren't trained to recognize their subtle but important implications. NASA's follow-up statement, released 12 hours after closest approach, provided technical details that satisfied scientific curiosity while frustrating public expectations for dramatic revelation. Preliminary analysis of Mars orbital data indicates minor variations in ionospheric density, consistent with expected interactions between Atlas's ion tail and Mars's magnetosphere. No structural damage to orbital assets detected. Surface operations continuing nominally. The language was precise, professional, and utterly devoid of the cosmic drama that months of speculation had led the public to expect. Where were the stunning images of Atlas blazing past Mars? Where were the electromagnetic light shows that should have been visible from Earth-based telescopes? Where were the obvious signs that something historically significant had occurred? The disappointing reality was that most of the dramatic phenomena people expected would have been largely invisible to casual observation. Ionospheric density variations, while scientifically important, don't produce visual spectacles that translate well to social media. Magnetosphere interactions, however significant for understanding interstellar object behavior, generate data rather than imagery that captures public imagination. Professional astronomers understood that the most important consequences of Atlas's Mars encounter might not become apparent for months or even years. The subtle gravitational perturbations, the trace atmospheric chemistry changes, the long-term effects on Mars's electromagnetic environment, all of these required careful analysis of data that would be collected over extended observation periods, processed through peer review, and published in journals that few members of the public would ever read. But public attention operates according to news cycle dynamics that demand immediate gratification and clear resolution. The story of Atlas, which had sustained media interest for months through mystery and speculation, suddenly lost its narrative momentum when the October 3rd encounter failed to provide obvious drama. Cable news networks found themselves with hours of prepared Atlas coverage and very little dramatic content to justify the airtime they had allocated. The absence of spectacle created an information vacuum that conspiracy theories rushed to fill with explanations that satisfied psychological needs that scientific reality had failed to address. If nothing dramatic had occurred, skeptics argued, why had space agencies been so secretive about their observational plans? Why were there so few publicly released images from the encounter? Why did official statements sound like they were hiding something behind technical jargon and institutional caution? Amateur astronomers who had spent weeks preparing for the encounter found themselves in the awkward position of having captured images that showed nothing particularly remarkable. Their telescopes had documented Atlas's passage near Mars, but the visual evidence looked disappointingly similar to computational predictions that had been available for months. The most sophisticated ground-based observatories faced similar challenges in translating their data into public understanding. The spectroscopic measurements that revealed subtle changes in Atlas's emission patterns were scientifically valuable but visually unimpressive. Radio telescope arrays detected variations in plasma density around Mars, but these discoveries couldn't be easily converted into the kind of dramatic imagery that captures public imagination and generates viral social media content. Social media algorithms, designed to promote engagement rather than education, began amplifying increasingly elaborate theories about what space agencies weren't telling the public. The mundane reality of a successful scientific observation campaign was reframed as evidence of institutional secrecy. The careful, methodical approach that characterizes professional astronomy was interpreted as deliberate obfuscation designed to hide dramatic discoveries from public scrutiny. Congressional representatives, many of whom had used Atlas as a platform for discussing space funding and planetary defense, found themselves in the uncomfortable position of having promised their constituents dramatic revelations that failed to materialize. House Science Committee hearings that had been scheduled to address the Atlas crisis were hastily rebranded as routine oversight sessions on NASA's Mars exploration programs. The media coverage reflected this shift from crisis to anticlimax with remarkable speed. Cable news networks that had prepared extensive Atlas encounter programming found themselves with expert panels assembled to discuss cosmic catastrophes, instead explaining why the absence of drama was actually the most likely outcome. The successful prediction of a non-catastrophic encounter was somehow less compelling than unsuccessful predictions of disaster would have been. The scientific community faced its own public relations challenges. Researchers who had spent months preparing for Atlas observations found that their preliminary results, while scientifically interesting, didn't generate the kind of public excitement that translates into continued funding support and sustained public interest in space exploration. International cooperation in Atlas observations, which had represented one of the most comprehensive multinational astronomical campaigns in history, received minimal media coverage precisely because it had functioned so smoothly. The coordination between NASA, ESA, JAXA, and other space agencies had prevented the kind of conflicting information releases that might have sustained public interest through controversy and competing interpretations. The James Webb Space Telescope's infrared observations of Atlas during the Mars encounter produced some of the highest resolution images of an interstellar comet ever captured, representing genuine scientific triumphs that advanced our understanding of these cosmic visitors. But these scientific achievements were overshadowed by public disappointment that the images didn't show obvious signs of cosmic catastrophe or dramatic transformation. Amateur radio operators who had prepared to monitor Mars communication networks for signs of electromagnetic disruption found themselves documenting routine spacecraft operations instead of cosmic chaos. Their sophisticated monitoring setups, established to capture evidence of historical significance, instead recorded the mundane but reassuring normalcy of continued Mars exploration activities. The October 3rd non-event began to take on symbolic significance that transcended its astronomical importance. Social critics pointed to the Atlas anticlimax as evidence of broader institutional failures in science communication, arguing that researchers and space agencies had failed to properly manage public expectations for what was always most likely to be a scientifically interesting but visually unremarkable event. Educational institutions found themselves grappling with student disappointment that mirrored the broader public reaction. Astronomy classes that had been following Atlas for months as a real-time case study in interstellar object behavior found their students losing interest once the encounter failed to produce obvious drama. Teachers struggled to maintain engagement with the subtle but important scientific discoveries that the encounter had actually generated. The long-term implications for public support of space science became a source of concern within the astronomical community. If the most dramatic interstellar visitor in recorded history could pass through the inner solar system without generating sustained public interest, how would future missions compete for attention and funding against more immediately compelling terrestrial concerns? Yet perhaps most troubling was the speed with which public attention shifted from Atlas to other topics once the encounter proved less dramatic than expected. The Comet, which had dominated astronomical news cycles for months, virtually disappeared from mainstream media coverage within weeks of its Mars encounter. The scientific analysis of the encounter data, which would ultimately prove far more valuable than any dramatic impact scenario, proceeded largely outside public awareness. But this rapid shift in attention may have blinded us to subtle signs that Atlas's influence on our solar system was far from over. What if the quiet passage near Mars was merely the opening movement in a longer, more complex cosmic symphony? What if the real story of Atlas was just beginning, hidden behind layers of institutional secrecy and public indifference that prevented us from recognizing the true significance of humanity's first detailed encounter with a messenger from another star? Throughout human history, comets have served as cosmic punctuation marks in the narrative of civilization, harbingers of change, omens of transformation, messengers from realms beyond terrestrial comprehension that demand interpretation. by those wise enough to read the language of the heavens. Ancient astronomers interpreted their appearances as communications from divine powers, warnings encoded in celestial fire that carried implications for kingdoms and civilizations across the known world. Atlas arrives in our solar system carrying credentials that no previous comet has possessed. This is not a familiar member of our Sun's extended family, following predictable orbits that can be calculated decades in advance and explained through well-understood gravitational mechanics. This is a genuine alien, a visitor from stellar distances, so vast that it carries within its nucleus the chemical signatures of stellar environments that may no longer exist, stellar systems that died before Earth's continents assumed their current configurations. The message that Atlas carries is written in a language older than terrestrial biology, the language of atomic structure and molecular bonds, of isotopic ratios and crystalline matrices that formed under conditions that never existed anywhere in our solar system. Every spectroscopic analysis of Atlas's emissions reveals chemical signatures that tell stories of alien stellar winds, exotic radiation environments, and gravitational conditions that shaped matter according to physical laws operating at extremes our solar system has never experienced. But what if Atlas's message transcends mere chemistry? What if the patterns we've been observing, the erratic brightness variations, the unusual coma geometry, the unexpectedly massive carbon dioxide emissions, represent something more structured than random comet behavior? What if we're witnessing the first attempts at interstellar communication using a medium we never thought to monitor the controlled sublimation of exotic ices, arranged in patterns that create detectable signals across interstellar distances? Consider the possibility that intelligence could manipulate cometary emissions in ways that create detectable patterns across the vast emptiness between stars. A civilization that had mastered large-scale engineering might be capable of embedding information in the orbital and emission characteristics of objects launched between stellar systems, creating slow-motion signals that would eventually be detectable by any technological civilization monitoring their solar system for unusual phenomena. The mathematics of such communication would be elegant in their simplicity. Binary information could be encoded in brightness, variations that follow patterns distinguishable from natural fluctuations. Complex data could be embedded in spectroscopic signatures that reveal themselves only through careful analysis of emission line ratios over extended observation periods. Even the object's trajectory could carry information, with subtle course corrections during approach creating geometric patterns that would be unmistakable signatures of artificial control. Atlas's behavior, viewed from this perspective, takes on new significance that transforms months of astronomical observations into potential archaeological excavation of an interstellar message. The massive carbon dioxide coma that has puzzled astronomers could represent not just unusual sublimation, but controlled gas release designed to maximize the object's visibility and ensure detection by technological civilizations at precisely the right stage of their development. The erratic brightness patterns that don't match standard comet models could be structured signals waiting for proper mathematical analysis to reveal their embedded message. The timing of Atlas's arrival, during a period when humanity has finally developed the technological sophistication to conduct detailed spectroscopic analysis of interstellar objects, might be more than cosmic coincidence. If the object were launched from its origin star system thousands of years ago, its trajectory would have been calculated to arrive at our solar system during a narrow window, when our technological development made us capable of receiving and interpreting sophisticated chemical messages encoded in cometary emissions. The launch timing would have required precise knowledge of our star system and remarkable patience in executing a communication strategy that spans millennia. NASA's James Webb Space Telescope represents humanity's most advanced instrument for analyzing the chemical composition of distant objects. The timing of Atlas's arrival, just as this revolutionary observatory becomes operational, creates conditions where we can extract more information from a single interstellar visitor than would have been possible even a decade earlier. If Atlas carries an embedded message, we may be the first generation of humans capable of decoding it. The European Space Agency's coordinated observation campaigns have generated datasets that contain more information about an individual interstellar object than has ever been collected in human history. Hidden within the terabytes of spectroscopic data, orbital measurements and emission analysis might be patterns that reveal themselves only through computational analysis techniques that didn't exist when previous interstellar visitors like Oumuamua passed through our solar system. But decoding a potential interstellar message requires abandoning anthropocentric assumptions about communication protocols. The signals might be embedded in mathematical relationships that transcend language barriers, prime number sequences hidden in brightness, variations, geometric constants encoded in spectral line ratios, physical constants expressed through isotopic compositions that could only result from artificial manipulation of matter under controlled stellar conditions. The challenge lies in distinguishing between natural patterns and artificial signals in phenomena that already stretch the boundaries of our understanding. Interstellar objects inherently exhibit behavior that doesn't match solar system norms because they formed under different stellar conditions and follow different evolutionary paths. Separating genuine anomalies from exotic but natural processes requires analytical techniques that are still being developed. Amateur astronomers and citizen science groups have been contributing observational data that professional observatories might miss due to scheduling constraints and limited telescope time. If ATLAS carries embedded signals, they might be most apparent in long-term monitoring data, collected by dedicated amateur observers who can track the object continuously, rather than during brief professional observation windows dictated by institutional priorities. The SETI Institute has quietly begun applying signal analysis techniques developed for radio astronomy to the ATLAS datasets, searching for patterns that might indicate artificial manipulation of the object's behavior. While no results have been publicly announced, the mere fact that such analysis is being conducted suggests that the possibility of ATLAS serving as an interstellar communications platform is being taken seriously by researchers experienced in searching for extraterrestrial intelligence. The message, if it exists, might not be intended for immediate comprehension. Interstellar communication across thousands of years would necessarily involve concepts and information that might require generations of human technological development to fully understand. ATLAS might be delivering a message that will only become comprehensible when our mathematical and scientific knowledge advances to levels that match the civilization that sent it. The psychological implications of such a discovery would transform human civilization in ways that dwarf any physical effects ATLAS might have on Mars or other planets. Confirmation that we are not alone in the universe, delivered through the patient arrival of an interstellar message, would force humanity to reconceptualize our place in the cosmic community and our responsibilities as members of a galaxy-spanning network of intelligent civilizations. But the absence of an obvious message shouldn't be interpreted as evidence that no message exists. The most sophisticated communication might be embedded in aspects of ATLAS's behavior that will only become apparent through analysis techniques that haven't been invented yet. Future generations might look back at our current ATLAS observations and marvel at how much information we failed to extract from the richest interstellar dataset in human history. International cooperation in ATLAS research has created unprecedented opportunities for global collaboration in potential message decoding efforts. If the object carries information intended for all of humanity, rather than any single nation, the distributed nature of current observation campaigns ensures that no single government or institution could suppress or monopolize access to interstellar intelligence. The ATLAS encounter might be serving as an inadvertent test of our civilization's capacity for rational analysis under conditions of uncertainty and speculation. Our response to this interstellar visitor, the theories we've generated, the fears we've expressed, the institutions we've trusted or suspected, might reveal fundamental weaknesses in our collective decision-making processes that could prove catastrophic when genuine cosmic threats eventually emerge. The speed with which ATLAS became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence suggests that we've developed information processing systems that are more vulnerable to manipulation than we realized. Social media algorithms that amplify dramatic content over accurate content have created conditions where speculation can overwhelm evidence faster than scientific analysis can counter misinformation. Yet the most profound realization emerging from the ATLAS encounter is temporal, that our solar system exists within galactic neighborhoods where interstellar visitors are routine rather than extraordinary events. The rarity of such objects in human historical records reflects not their actual scarcity but the brief duration of our technological civilization relative to astronomical timescales. If ATLAS represents the first of many interstellar visitors that our expanding detection capabilities will identify in coming decades, then our current speculation and institutional responses might be establishing precedents for how humanity will address an entire class of cosmic encounters. The frameworks we develop for analyzing ATLAS, both scientific and social, will shape our responses to future interstellar visitors for generations to come. Perhaps Atlas's greatest gift to humanity isn't any specific message it might carry, but the mirror it holds up to our civilization, reflecting our readiness, or lack thereof, for membership in whatever cosmic community exists among the stars. What if we're missing the real story entirely? October 3rd has passed into history as a date marked more by anticlimax than apocalypse. But in the quiet aftermath of an encounter that failed to deliver the cosmic drama that months of speculation had promised, a more unsettling possibility begins to emerge from the shadows of institutional behavior and information management. What if our entire framework for understanding Atlas, our focus on impact scenarios, atmospheric disruptions, and potential contamination, represents a fundamental misunderstanding of what we're actually witnessing? What if the real story of Atlas isn't about what might happen to Mars, but about what has already happened to our information systems, our decision-making processes, and our collective ability to distinguish between genuine cosmic threats and manufactured crises designed to test or manipulate public opinion and institutional responses? The evidence for this alternative interpretation lies not in telescopic data or spacecraft telemetry, but in the patterns of institutional behavior that have surrounded Atlas since its discovery. Consider the careful timing of information releases, the unusual coordination between international space agencies that normally compete for resources and recognition, the conspicuous level of congressional interest in what should have been a routine astronomical observation campaign. Space agencies that typically rush to publicize their most dramatic discoveries have been conspicuously measured in their Atlas communications. The James Webb Space Telescope's observations of the object, conducted in August, remain under analysis. Months later, despite the revolutionary capabilities of the instrument and the presumed significance of studying humanity's first well-documented interstellar visitor with such sophisticated equipment, NASA's Science Mission Directorate, normally eager to share spectacular images and breakthrough discoveries with tax-paying publics, has provided primarily technical briefings and trajectory updates, rather than the kind of inspirational content that typically accompanies major astronomical events. The European Space Agency, with its different political constraints and communication traditions, has followed remarkably similar protocols, suggesting coordination that transcends normal institutional boundaries. The absence of spectacular imagery from the October 3rd encounter might not represent a failure of observation campaigns, but the success of information management strategies that were not meant to recognize as such. If the most significant aspects of Atlas's passage near Mars occurred in spectral bands or at temporal resolutions that don't translate into publicly compelling content, the lack of dramatic footage could be entirely intentional. Professional astronomers, who normally compete vigorously for publication priority and media attention when dealing with significant discoveries, have maintained an unusual level of collective discretion regarding Atlas research. Preliminary findings that would typically be announced at press conferences and published in rapid-release journals have instead followed more deliberate review processes that prioritize institutional coordination over individual recognition. The amateur astronomy community, typically eager to share observations that might challenge or complement professional research, has produced surprisingly little independent analysis of Atlas, despite the object's accessibility to sophisticated backyard equipment. This silence might reflect not lack of interest, but pressure from professional networks to coordinate observations rather than compete for attention and recognition. Congressional oversight of space agencies, while publicly focused on routine budgetary and policy questions, may be addressing classified aspects of Atlas research that never appear in public hearing transcripts. The space science committees that normally micromanage NASA's most expensive missions have shown unusual deference to agency expertise regarding Atlas observation strategies and data release schedules. International space law provides frameworks for managing information about potentially hazardous objects, but these protocols were developed with conventional near-Earth asteroids in mind, not interstellar visitors whose origins and compositions might reveal information that transcends normal astronomical significance. If Atlas carries implications for national security or international relations, existing treaties might not provide adequate guidance for information management. The possibility that we're witnessing the first coordinated global response to an interstellar visitor carrying information too sensitive for routine public disclosure would explain many of the anomalies in official Atlas coverage. Space agencies, intelligence services, and political institutions might be navigating unprecedented challenges, that have no historical precedents and no established protocols for managing information that could fundamentally alter humanity's understanding of our place in the universe. But information control, if it exists, might serve purposes beyond simple secrecy. If Atlas carries embedded messages or technological information that humanity is not yet prepared to understand or utilize safely, managed disclosure might represent responsible stewardship rather than institutional deception. The gradual release of increasingly complex information might be designed to prepare global civilization for revelations that could be destabilizing if delivered without proper preparation. The timeline for such managed disclosure could span decades, with each phase of revelation calibrated to match humanity's technological and social development. The current focus on Atlas as an interesting but ultimately routine astronomical phenomenon might represent the opening phase of a much longer educational process designed to prepare us for eventual recognition of the object's true significance. Educational institutions and scientific organizations might be quietly preparing curricula and research programs that will eventually address the implications of interstellar communication and cosmic citizenship, but only after political and social institutions develop frameworks for managing such profound expansions of human knowledge. The apparent normalcy of current Atlas research might conceal preparation for extraordinary future revelations. Yet even managed disclosure assumes that Atlas carries information or implications significant enough to justify such elaborate coordination. What if the most disturbing possibility is simpler, that Atlas represents exactly what conventional astronomy suggests? A routine interstellar object following predictable physical laws, and our tendency to seek hidden significance reveals dangerous vulnerabilities in our information processing systems. The readiness with which conspiracy theories and alternative narratives have attached themselves to Atlas might indicate that our technological civilization has become dangerously susceptible to disinformation campaigns that exploit our psychological need for cosmic significance. If a genuinely routine astronomical event can generate such elaborate speculation, how would we respond to actual cosmic threats or legitimate interstellar messages? The Atlas encounter might be serving as an inadvertent test of our civilization's capacity for rational analysis under conditions of uncertainty and speculation. Our response to this interstellar visitor, the theories we've generated, the fears we've expressed, the institutions we've trusted or suspected, might reveal fundamental weaknesses in our collective decision-making processes that could prove catastrophic when genuine cosmic threats eventually emerge. The speed with which Atlas became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence suggests that we've developed information processing systems that are more vulnerable to manipulation than we realized. Social media algorithms that amplify dramatic content over accurate content have created conditions where speculation can overwhelm evidence faster than scientific analysis can counter misinformation. Perhaps the most profound question raised by the Atlas encounter isn't what the comet might do to Mars, but what it has already revealed about humanity's readiness for cosmic citizenship. Are we prepared to handle information that challenges our understanding of our place in the universe? Can we distinguish between genuine mysteries and manufactured controversies? Do our institutions possess the wisdom and integrity necessary to manage discoveries that could reshape human civilization? The hidden truth about Atlas might be that there is no hidden truth, that the most significant cosmic encounter in human history is unfolding exactly as it appears, through routine scientific observation and analysis that reveals wonders and mysteries without requiring conspiracy theories or cover-ups to explain their significance. The real test might be whether we can accept the genuine mystery of an interstellar visitor without transforming it into something more dramatic than the universe has provided. Or perhaps the hidden truth is that Atlas represents our graduation from a solar system-scale civilization to participants in galactic-scale phenomena, and the test isn't about what the comet does to Mars, but about what our response to its presence reveals about our readiness for the larger cosmic community that awaits our membership. Sometimes the most profound revelations come not in the form of dramatic catastrophes or spectacular discoveries, but in the quiet realization that we've been looking in all the wrong places for all the wrong things. Atlas may have given us exactly what we needed to survive as a spacefaring species, we just haven't figured out what that gift was yet. The worst-case scenario isn't that Atlas destroys Mars, it's that Atlas saves humanity, and we never even notice. As this interstellar wanderer continues its journey toward the outer solar system, and eventually back to interstellar space, it carries with it not just the chemical signatures of an alien stellar environment, but also the reflected light and radio emissions from a young technological civilization taking its first tentative steps toward cosmic maturity. Future interstellar visitors might detect these signatures and draw their own conclusions about humanity's readiness for membership in whatever cosmic community exists among the stars. The Atlas encounter represents humanity's graduation from a solar system-scale civilization to participants in galactic-scale phenomena. Whether we've passed or failed this cosmic examination might not become apparent for decades, but our response to this first major test will establish patterns that influence our species' development for generations to come. Consider what Atlas has actually accomplished during its passage through our solar system. It has forced humanity to confront our cosmic isolation in ways that purely theoretical discussions never could. The simple existence of an object from another stellar system has made interstellar space seem less empty and alien civilizations seem more possible. Public opinion polls conducted during Atlas's approach have documented shifting attitudes towards space exploration, funding for planetary defense programs, and international cooperation in scientific research. These attitudinal changes, triggered by a single cosmic event, might influence policy decisions and resource allocation for decades to come. The Atlas encounter has also revealed the extent to which modern technological civilization depends on predictable cosmic conditions. Our spacecraft, communication systems, and even terrestrial infrastructure were designed under the assumption that space remains essentially static between major solar storms and asteroid impacts. Interstellar visitors introduce additional variables that our engineering and risk assessment systems weren't designed to accommodate. Future space missions will need to account for the possibility of encountering debris fields, electromagnetic anomalies, or chemical contamination left behind by interstellar visitors. Mission planning protocols that worked adequately for solar system exploration might prove insufficient for operating in a cosmic environment that includes regular interstellar traffic. The legal and ethical frameworks that govern space exploration were crafted under the assumption that cosmic encounters would involve objects and phenomena that originated within our solar system. Atlas has introduced questions about sovereignty, environmental protection, and scientific responsibility that existing space law doesn't adequately address. If future interstellar visitors carry embedded messages, technological artifacts, or biological materials, humanity will need new international agreements that balance scientific investigation with planetary protection, national security concerns with information sharing, and immediate research opportunities with long-term consequences for human civilization. The international cooperation that Atlas has inspired among space agencies, research institutions, and amateur astronomy communities represents an unprecedented experiment in global coordination around cosmic phenomena. The protocols developed for sharing Atlas data and coordinating observation campaigns might serve as templates for managing future encounters with interstellar visitors or other cosmic events that transcend national boundaries. But cooperation also creates vulnerabilities. If our current Atlas research is missing crucial information or misinterpreting significant patterns, the coordinated nature of current efforts might amplify these errors across multiple institutions and nations. The same coordination that makes comprehensive analysis possible could also make systematic mistakes more difficult to recognize and correct. The amateur astronomy contributions to Atlas research have demonstrated the continuing importance of distributed observation networks that can monitor objects continuously rather than during brief professional telescope windows. Future interstellar visitors might be best studied through coordinated campaigns that combine professional capabilities with amateur dedication and geographic distribution. Educational institutions that have used Atlas as a real-time case study in interstellar object behavior have created pedagogical resources that will influence how future generations of scientists approach cosmic mysteries. The teaching materials, observation protocols, and analytical techniques developed during Atlas research will shape scientific education for decades to come. The psychological and cultural impacts of Atlas might prove as enduring as its scientific contributions. This interstellar visitor has forced humanity to confront our cosmic isolation in ways that purely theoretical discussions never could. The simple existence of an object from another stellar system has made interstellar space seem less empty and alien civilizations seem more possible. The datasets generated by Atlas observations will continue providing research opportunities long after the object itself has departed our solar system. The spectroscopic measurements, orbital calculations, and emission analyses represent the most comprehensive study of an interstellar object ever conducted by human civilization. Hidden within these data might be insights that will only become apparent when future technological developments provide new analytical capabilities. Graduate students and researchers decades from now might discover patterns in the Atlas data that reveal information we currently lack the mathematical or theoretical frameworks to recognize. The most significant discoveries from Atlas's visit to our solar system might not emerge until the 2040s or beyond, when scientific advances allow us to extract information from observations we're conducting today without fully understanding their ultimate implications. Perhaps most importantly, Atlas has served as a mirror that reflects our civilization's relationship with the unknown, our trust in expertise, and our ability to distinguish between genuine mysteries and manufactured crises. The lessons we draw from Atlas's passage through our solar system might prove more significant than any physical effects the object has on Mars or other planets. The speed with which Atlas became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence reveals fundamental characteristics of how our species processes information about phenomena that challenge our understanding. These patterns will shape our responses to future cosmic encounters, potentially determining whether humanity approaches such events with rational analysis or succumbs to speculation and fear. October 3, 2025, might be remembered not as the day Mars was threatened by an ominous interstellar visitor, but as the day humanity began to understand that we are not alone in a universe full of wandering messengers carrying news from distant worlds. The real question isn't what Atlas might do to Mars, but what it has already done to us, and whether we're prepared for the next cosmic visitor that follows in its ancient starlit wake. The silence that follows October 3rd might be the most ominous sound in human history, not the silence of space which we've always known was there, but the silence of missed opportunities, ignored warnings, and questions we were too afraid to ask. In that silence, Atlas continues its journey back to the stars, carrying with it the fading radio signatures of a young civilization that had its first chance to prove it was ready for cosmic citizenship. Whether we passed that test remains to be seen. The universe, patient and indifferent, will undoubtedly provide more opportunities. The question is whether we'll recognize them when they arrive, or whether we'll continue to mistake the most important messages for background noise in the cosmic symphony that plays eternally around us. The worst-case scenario for Atlas might not be planetary catastrophe or electromagnetic chaos. It might be that we've learnt nothing from this encounter about our cosmic vulnerability, our institutional limitations, and our desperate need to develop better frameworks for understanding our place in a universe that is far stranger, far more active, and far more dangerous than our brief technological civilization has yet realized. But perhaps that's exactly the lesson Atlas came to teach us, that the universe doesn't owe us dramatic revelations or comfortable answers, that cosmic citizenship requires patience, wisdom, and the humility to recognize that sometimes the most important messages arrive not as thunderbolts from the sky, but as whispers in the cosmic wind that only those who know how to listen can hear. In the end, Atlas may have accomplished something far more valuable than destruction or discovery. It may have given humanity its first glimpse of what it means to live in a universe where we are not alone, where cosmic visitors carry messages we're still learning to read, and where our survival as a species depends not on our ability to dominate the cosmos, but on our wisdom to understand our place within it. The journey continues. The universe watches, and somewhere in the darkness between the stars, other messengers begin their own long voyages toward distant worlds, carrying within their ancient nuclei the hopes and warnings of civilizations we have yet to imagine.